Hi, and welcome to section 3 of this course, where we take a look at image manipulations. So image manipulations cover a wide range of topics, as you can see here. However, they're all very important in understanding the foundations of OpenCV. So we're first going to take a look at some simple transforms, then do some simple operations, which includes the ever important thresholding and edge detection, which actually forms the foundation of the first mini project you're going to complete, which is making a live sketch of yourself. So let's talk a bit about transformations. So what exactly are transformations? Simply put, they're geometric distortions enacted upon an image. Now these distortions can be simple. It can be things like resizing, rotation, translation. However, there are more complicated distortions such as perspective issues arising from different views that an image was captured from. So we classify transformations into two main categories in computer vision: affine and non-affine. So let's talk a bit about affine and non-affine transformations. Now, affine transformations include things such as scaling, rotation, and translation. And the key point to note here is that lines that were parallel in the original images are also parallel in these transformed images. So whether you scale an image, rotate, or translate, parallelism between lines are always maintained. Not so in non-affine transformations, which are also known as projective and homography transforms. As you can see here, these lines are no longer parallel in this transformed image here. However, in non-affine transformations, collinearity and incidence is maintained. What is collinearity? What that means is that if all the points on this line here remain still on this line, and vice versa. It's also important to note that non-affine transformations are very common in computer vision, and they actually originate from different camera angles. So imagine you were facing this square from a top-down view. However, you begin to move the camera this way. You can imagine your viewpoint would now be skewed. You'd actually be seeing these 2 points closer together while these two further apart. That is how non-affine transformations come about. And there are ways in computer vision that we correct these, which we'll come to shortly. So let's now actually implement some of these transformations in OpenCV code. So let's talk a bit about translations. Transitions are actually very simple, and it's basically moving an image in one direction. It can be left, right, up, down, or even diagonal if we implement an X and Y translation at the same time. So to perform a translation, we actually use OpenCV's CV2 warp affine function, but that function requires what we call the translation matrix. So without getting into too much high school geometry, a translation matrix basically is in this form and takes an X and Y value as these elements here. Now what this represents here is a shift along the X-axis horizontally, and Y is a shift along the Y-axis vertically, and these are the directions each shift takes place. So images always start off being at the top left corner, and we translate it in any direction using the translation matrix here. So let's implement this in code quickly. So let's implement translations using OpenCV now. So going through line by line, I'll quickly show you what's being done here. The important thing to note is that we're using the CV2 warp affine function, and that's being implemented down here. So quickly going through, we load the image as we've done before. We extract the height and the width of the image using the NumPy shape function, taking only the first two elements of the shape array that it returns. Next, I have a line here where we extract quarter of the height and quarter of the width. That's going to be our TX and TY value in our translation matrix. That's the direction, the amount of pixels we're going to shift the image. And we actually use NumPy float 32. That actually defines the array, the data type for our translation matrix. And by using some square brackets here, we actually created our T matrix here. It may or may not be important for you to understand this, but just take note of the form of this T matrix here. So the warp affine function takes our image that we loaded in, the T matrix that we created, and our width and height as a tuple. And it actually returns the translated image. So let's actually run this and see what it looks like. Ta-da! This is our translated image here. As you can see, it shifted the image in the X direction, a quarter of the initial dimensions, and similarly for the Y dimension, but just downward. So it's important to note that we should just take a look at the T matrix to give you an understanding of what we have done here. So this is exactly what we wanted in our T matrix. It's 1, 0 in this order, and tx and ty, this being a quarter of the height and a quarter of the width, respectively. So let's talk a bit about rotations. Now rotations are pretty simple as well, however there are some more quirks that I'll teach you quickly. So using our favorite politician again, Donald Trump, we can illustrate exactly what a rotation is. So as you can see, it rotates about a point, and this point here in this image is the center, and it just turns the image around that point. So imagine that point as a pivot. So similarly, in our transformation, we had a T matrix, now we have an M matrix, which is the shorthand used for the rotation matrix. Theta here is the angle of rotation. As you can see, it's an anti-clockwise angle measured from this point here. And one important thing to note is that the OpenCV function, which is get rotation matrix 2D, actually does scaling and rotation at the same time, which you will see in the code. So let's implement some rotations using OpenCV. So rotations are very similar to translations in that we actually have to generate a transformation matrix, what we call the rotation matrix here. And to do that, we actually use an OpenCV function called getRotationMatrix2D. Now this function is fairly simple as well. What you give it is, first argument is the center, the x and the y center, which corresponds to width and height. That's the center point of the image in most cases. However, you can and you are free to rotate amongst any point in the image for whatever reason that may be. This is the theta, which is the angle of rotation. Remember, it's anti-clockwise, and this is a scaling factor, which I'll bring up shortly. And we use this rotation matrix again in the OpenCV warp affine function. So let's run this code, see what it looks like. There we go. So that's our image rotated 90 degrees anti-clockwise. And you may have noticed that the top and bottom parts of the image are cropped, mainly because the canvas size remains the same. So there are two ways we can fix that. One, let's adjust the scale here. So let's put this at 0.5. There we go. However, there's a lot of black space around this image. Now to avoid that, you would actually have to put the specific width and heights of the new rotated image. So whatever you anticipate it to be, you can program it here. However, that's not often, well, it's a bit tedious to do sometimes unless you have a special case for it. There's another way we can do it, and that's by using the transpose function here. Now the transpose function, let's run this code and see what happens. It actually transposes the image 100%. Now you may not see the bottom because it's cut off from the screencasting software here. However, the image is fully done and rotated here anti-clockwise, and there's no black space around it. So this is just another easy and convenient way of rotating images. However, it only does it in 90 degrees increments at one time. So you can play around with this and actually do some cool rotations without having to actually program the new width and the new height of the new canvas. So moving on to another simple affine transformation is resizing, also called scaling. And resizing, you may think, is actually quite simple. However, it involves something called interpolation. And interpolation is basically when we resize an image, imagine you're expanding points or pixels. So when you resize an image from small to big, how do we find the gaps in between those little pixels? So that's what interpolation is. And I've just drawn this simple little diagram here to show you with GPS coordinates, because when you're doing GPS tracking, you actually interpolate points quite a bit. So imagine the red points are pixels, and these are the actual pixels here. Now imagine before, these pixels were closer together, the red pixels. Ignore the yellow pixels and the green pixel for now. So we just have red pixels that are closer together. But now we've stretched them out, and we need to approximate the pixels in between. That's what interpolation is. Interpolation is the method we use to actually put or generate these pixels here. So as you can see in a GPS type example, going up in a straight line north, putting a pixel here is a fairly good idea. However, doing this linear meaning straight line joining between pixels, we actually don't reflect that maybe the vehicle took a corner here. Instead, the vehicle drove maybe straight to some buildings here in this dumb example. And that's a form of interpolation which we call linear interpolation. So let's talk a bit about the types of interpolations here. is inter-area, nearest, linear, cubic, and Lanczos 4, apparently. So these are all methods, and I won't go into details here. There's actually a very good comparison on this link here. But generally, inter-area is good for shrinking or downsampling images. That's actually another form of interpolation as well. Probably just what this does is it merges the pixels within the area. That's why it's good for downsampling. Inter-nearest is the fastest algorithm according to this comparison here. Linear is good, as in this case it's a linear interpolation here. It's typically good and it's the default method used in zooming. However, intercubic, which is probably what's going to generate this green point here, is definitely better. And Lanczos, or Lanczos, is actually the best. So you can check them out here. So let's actually implement this in some code now. So let's now implement some simple scaling or resizing in OpenCV. So OpenCV uses the cv2.resize function with the arguments listed up here. But let's actually use this function to get a feel of it. So firstly we load our image, and then using the resize function, it takes our input image, none, which I'll discuss later on shortly, fx and fy. These are the factors we want to scale by. So what we're telling it here is that we want to scale our image by 3/4, so 3/4 the original size. And the reason we set it at the same 0.75 here is that we want to maintain our image ratios. So by default I said it uses interlinear as its interpolation method. We're actually going to try intercubic, inter-area, and we're actually going to change the dimensions here that we resize to. So this actually allows us to resize exactly the dimensions we want. So you'll understand that shortly when we actually implement this code. So let's run this code now. As you can see, this is the picture of the Louvre I took, and it's actually smaller than the original images by 3/4 its size. This one is much bigger, this is twice its size, and this is using the intercubic, which is actually a slower method of interpolation. However, the resizing looks decent quality as well. And this is the one that's skewed, so we actually set the dimensions here. So let's bring this into this view here. So we actually set the width to be 900 and the height to be 400, as I previously showed in the code here. Similarly, we can actually skew in one dimension, or I should say resize differently in one dimension. So we implement something that looks like this here, which is sort of compressed horizontally here. Okay, so that's it for resizing. It's actually a pretty basic function. So we'll now move on to some other topics in OpenCV. So we're going to take a look at a technique, another technique for resizing I should say, called image pyramiding. And what that is, it's shrinking or enlarging multiple copies of an image, as we can see right here. And what that does, it basically allows us to create multiple scales of an image, several scales, several versions in fact. And that's quite useful in object detection when you want to be resilient to different scales of an object. So let's look at implementing this in our code. So the code for implementing image pyramids is actually quite simple, and the bulk of the work is just done in this function here, which is pi down and pi, or pyr I should say, up. So what's happening here is that we load our input image, and pyr down actually converts in this image to an image that's half its size, or 50% the original dimensions. And vice versa, pyr up actually takes this image and makes it twice its size. So what's going to happen if we put smaller into a pi or pyr up function is that we're going to get back an image that is exactly the same dimensions as the original image, but you will see a key difference when I run this code. So here is a smaller image. As we expected, it's 50% smaller. However, when we run this smaller image into the larger image, you may be able to see it in the video here if your stream is good quality, but it actually is quite blurry, and that's because we're upscaling a smaller image here. So that shows you how with resizing images you actually tend to lose quality, so be careful with that sometimes. Okay, so that's it for image pyramiding. If you ever wanted to create multiple copies of a small image, you can actually put this into a loop, like a for loop or while loop, and maybe just run it a few times and it keeps generating smaller and smaller images. So cropping images is something fairly straightforward. I imagine most of you have done this in Microsoft Word or using your iPhone or any image editing software. It basically refers to extracting part of the image that you want, hence removing the excess. So in this example here, we just want the center of the rooftop of the Louvre here, and that's what we get here. So let's take a look at how we do this in OpenCV. So OpenCV actually doesn't have a direct cropping function. However, it's still easily done using NumPy, and that's done in this line right here. So what NumPy allows us to do is that we can put our image array right here, and then using the indexing tools, or I should say methods in NumPy, we define a start row to end row, then a start column to end column, and that separated by a comma, and that basically extracts the rectangle that we wanted wanted to crop out initially. So to define the start row and start column, we actually we load our height and width first, and we actually take 25% of the height and 25% of the width, and then 0.75, so 75% of the height and width. That gives us the exact center point of the Louvre, as you saw in this previous slide here. So I've just approximated what those dimensions should be. So by saying start row at 25% here, I've just said that this distance from here to here is 25%, and this distance from here to here is 75% of the image. And similarly for columns here. So you can play with those values if you want. You can enter actual pixel values. I just did this to make it a little easier to modify. So let's run this code and see how it works. So original image, and this is our cropped image. It actually works fairly well. So let's sort of try to overlay this here so you can actually understand a bit more what I did here. So by saying 25% row width here, I'm saying the start position of the rows you want to extract starts here. So that's 25% point, and the 75% point starts here. Actually, these are columns, not rows. And similarly with rows, 25% starts here. As you can see, it's 25% from here to here. And the 75% value starts from here to here. So that's exactly how we get this cropped image here. And if you ever need to use this cropped image for anything else, it actually stores it as cropped. Well, we store it as a cropped image here from our NumPy indexing, and that can be used for many other things going forward. So that's it for cropping. So let's get into some arithmetic operations using OpenCV. So what arithmetic operations are? They're basically adding matrices to our image array. And by adding matrices or subtracting matrices from our image array, it has the effect of increasing brightness or decreasing brightness or intensity. So to do that, we actually have to first create the matrix that we want to add or subtract to our image. And NumPy actually has some built-in functions, one called np1s. This allows us to create an array which is of this dimension, which is the same dimensions as our image here. And we assign the data type to unsigned integer 8, which is what OpenCV uses to store our image data. And we multiply it by a scalar 75. So if you wanted to see what this looks like, let's just copy this line here and run it separately in a different cell. And let's actually just print it here. And there we go. So as we see, it's a matrix of 75s here. Of course, it follows the same dimensions as this image here. So using the cv2.add function, it adds these two matrices here. Now to use this function, this and this image or array, I should say, has to have the same dimensions, which is why we followed and copied it into this np1's function here. And likewise, we do it with the subtraction function here. So let's see how this looks when we actually run this function. There we go. This is our darkened image here, substantially darker, and this is our brightened image here. What's important to know is that, let's say we did 175 here. What do you think would have happened? Let's run it again. This one is even darker, which means that values that were bigger than 175, these are the only ones that show up now because everything else goes to 0, which is why it's black. And similarly, there's a lot of white points or very light colors here. What happens is that when you add 175 to these points, it actually reaches 255, which is white. As you can see, it sort of has the effect of clipping highlights in some areas here. Please note that we can't ever exceed 0 and 255. So when we're adding matrices to our image array, keep that in mind, that you will get some clipping, which is what we saw in the black and in the white images here. So let's start doing some bitwise operations. And I call it bitwise operations and masking because that's essentially what you'll be using these bitwise operations for. They are quite handy when you have to mask images, which you'll see later on in this course, but for now we'll just introduce the topic. So firstly, let's create some shapes here. So we're going to create a square and an ellipse here. Now, you may be familiar with creating a rectangle or square, I call it here because it's the same dimensions side to side for this one. However, an ellipse is slightly different. It doesn't actually follow the same standard as a circle. You can check the OpenCV documentation to get some details. I won't go into it in this chapter here. It's going to take up too much time. However, let's just run this function and we see it here. So this ellipse or circle I've created here is actually not a full ellipse. I've set the parameters to create sort of a semi-hemisphere image here. So what we're going to do now, we're going to overlay these images and using some bitwise operations to illustrate the different type of operations that we have. So let's get to it. So let's start doing some bitwise operations. And I call it bitwise operations and masking because that's essentially what you'll be using these bitwise operations for. They are quite handy when you have to mask images, which you'll see later on in this course, but for now we'll just introduce the topic. So firstly, let's create some shapes here. So we're going to create a square and an ellipse here. Now, you may be familiar with creating a rectangle or square, I call it here because it's the same dimensions side to side for this one. However, an ellipse is slightly different. It doesn't actually follow the same standard as a circle. You can check the OpenCV documentation to get some details. I won't go into it in this chapter here. It's going to take up too much time. However, let's just run this function and we see it here. So this ellipse or circle I've created here is actually not a full ellipse. I've set the parameters to create sort of a semi-hemisphere type image here. So what we're going to do now, we're going to overlay these images and using some bitwise operations to illustrate the different type of operations that we have. So let's get to it. So let's actually run some bitwise operations on the images we just created. So by doing that, we use these OpenCV functions, bitwise AND, bitwise OR, bitwise XOR, and bitwise NOT. If you're familiar with logic gates or just general programming, you'd understand that what these things mean. However, it's always good to illustrate it in our images itself. Keep in mind that square and ellipse has to be of the same dimensions here, which is why we created the canvas initially at 300 by 300 pixels. So let's run this. So before we run this, let's just get a refresher of what our images look like. So let's run the AND command. What do you think is going to happen? Exactly. Well, I hope you assumed this would happen. This is the intersection of only those two images here. And by intersection, I mean these are the only white areas. And keep in mind these statements here, they work when you have a binary type image, either black or white. Otherwise, on a grayscale image, it's not exactly going to work like you imagine. You can try it on your own. However, I'm illustrating the concepts of these bitwise operations here. So this white area here is the only parts of those two images that intersected. So let's look at the OR bitwise operation. Exactly as we anticipated. Both images are shown here. So this sort of takes the circle and the square and merges them together here. Now the XOR. What do you think XOR is going to do? Let's see. XOR is sort of a weird one. It sort of looks like a reverse, sort of an intersection between these. So what this means here is that AND in an XOR goes back to 0 or black, and where it remains, where the images exist like an OR statement, it shows up here. So it can be useful for some things. You can maybe later on figure out what you may need it for. And now let's look at NOT. Now keep in mind NOT is different. NOT just takes one image into consideration. So a NOT is actually equivalent to an inverse of an image, and you'll see that shortly. So let's look at what that is. So let's bring it in here, minimize this one. So this is a square run in a bitwise NOT operation. As you can see, it basically inverts the colors, which is actually quite useful in many OpenCV functions, which you will come across later on. So that's our introduction to bitwise operations. Hope you found it useful. So moving on to convolutions and blurring. So the first thing to note here is that a convolution isn't an OpenCV function per se. It's an actual mathematical operation that's performed between two functions, and it produces a third function, which is obviously an output coming out of the original operation. So this is sort of illustrated here. We have an image here, then we run it by our function through a convolution, and our function here is of a certain kernel size. And what do we mean by kernel size? Well, this grid here represents a 10 by 10 image, or pixel image here. And this is a 5 by 5 kernel. So what this does here, the convolution basically operates at 1 pixel at a time. So I'm operating this kernel here at pixel 2, 2. So the convolution basically operates on this pixel, but it takes into consideration all the pixels around it in its calculation. You'll see why that's important when we get introduced to blurring, which is what we're about to do now. So, blurring is an operation, which you may have obviously figured out, that blurs an image. So you can clearly see here, this is a sharp picture of an elephant I took at Colchester Zoo. And this is the blurred image of the elephant. He's now, or actually she's now, quite blurry. So this is an example of a kernel matrix here. This matrix is 5 by 5, and we multiply our kernel matrix by 1 over 25. And that's how we normalize, that's called normalization of our kernel matrix, because we want all the elements in this matrix to sum to 1, which I mentioned here. Now, the first blurring method I'm going to introduce you to is OpenCV's filter 2D. It takes an image and runs it past the kernel here. So we're about to introduce that in our code, so let's go to our code and do so now. So let's look at this blurring in our code here. We're going to use the OpenCV filter 2D, which is the most basic form of blurring we can do in OpenCV. And we're going to do it by using a 3 by 3 kernel of 1s that we normalize by dividing by 9. So we're going to see the effects of blurring an image with a 3 by 3 kernel, and then by blurring it with a larger 7 by 7 kernel, which we also normalize by dividing by 49. So let's run this code and take a look at the blurring effects. This is our original image. You can see the elephant crease is quite clear, so it has a lot of detail in this image. So let's run it by the 3 by 3 kernel. And you can see it's definitely blurred. It's not a substantial amount of blurring, but it's definitely noticeable when you compare it to the original image. So let's now take a look at the 7 by 7. We expect a lot more heavy blurring, and that's exactly what we see. This is probably what a person who needs high prescription glasses might see. So that's our first blurring algorithm. We're going to take a look at a couple others now. Right, so if you scroll down over here, you'll actually see some more blurring functions that are available in OpenCV. So the first one we're going to use is actually a box filter. So it's called the CV2 blur function, and it's an averaging filter. What it does, it averages the pixels within a box that it runs through each pixel. So it puts the input image here, then it takes the kernel that we defined here, this is the box size, and averages out all the pixels here. So it sort of introduces a heavy blurring effect. It's actually quite a drastic blurring effect, which we'll see shortly. And that's why there's also the Gaussian blurring here. So what this does, instead of having a uniform box filter, it actually uses a Gaussian box filter. I'll show you what a Gaussian box is in the slides, but for now just imagine it's not going to have such a harsh effect as this blur function. Now median blur also uses a box filter type I mentioned here. However, it doesn't actually average out everything in the box. What it does, it finds a median value of all the pixels in that box, and then it actually puts median value as that pixel. So it's sort of a nice balance between this and averaging. This and Gaussian. And lastly, we have bilateral blurring. Bilateral blurring is actually quite useful, and what it does, it actually preserves it removes noise quite well and strengthens the edges in the image. So let's take a look and run this code and you'll see what I'm talking about. So this is an averaging box filter here. You can see it has pretty much a uniform type blurring effect. This is a Gaussian blurring here. Now the Gaussian blurring would actually, on the same size kernel, would actually be less blurring. But I've used a 7 by 7 in this example here. And this is the median blurring here. Now if you notice, median blurring sort of has a kind of painted type effect to it. And that's because it's finding the median value in little segments of the image. So if you wanted to ever introduce sort of like a painted type effect, maybe a median blur would be quite useful. And let's take a look at or bilateral blurring here. Now, as you can see in bilateral blurring, it's actually sort of a anti-aliasing type effect on this image. But what you can tell is that it definitely does preserve vertical and horizontal lines strongly here. But images like areas like the ears and different areas in the elephant is actually quite blurred. However, you can see vertical lines here are actually quite strong. So here's a slide summarizing those different types of blurring we just saw. So these are the same notes I just discussed here on each of the 4 blurring methods. However, I told you I'd show you what a Gaussian kernel looks like. And this is exactly what a Gaussian kernel is here. So you remember previously before in these other kernels, everything was the same value here. However, Gaussian kernels have a peak toward the center and they slowly peter off toward the edges here. This is sort of a 3D representation of what a Gaussian kernel looks like. And this is a matrix form here. And again, we normalize by a sum of all the elements here, which in this case is 273. So heading back to our IPython notebooks, there's one last image blurring method I just wish to discuss, and that's one called image denoising. This is the OpenCV function here. Fast N1 means denoising colored. It's quite a mouthful here. And what this does, this actually originates from computational photography methods. And as you know, using cell phone cameras and digital cameras, there's no way those tiny camera sensors can match the noise levels of complex, big DSLR cameras. So what they use to compensate is these complicated algorithms that sort of try to get the best or optimize the noise level so you don't see all the green in the image. So when we run this function, it actually takes some time, so I've just run it in the background. You get this nice, very clean looking image here. So that's the effects of running this algorithm. Now there's quite a few variations here. I won't get into the details exactly right now. These are some notes on the parameters here. This is filter strength, and these are some of the components you can play with. And that's it for blurring. Let's move on to sharpening, which is the opposite of blurring. So let's quickly discuss sharpening. Sharpening, as you imagine, is the opposite of blurring, and it actually strengthens and emphasizes the edges in an image. As you can see in this example of sharpening here, the edges here are normal, what you would see with your own eyes. However, in this image, all the edges here are much more pronounced, vertical, horizontal, edge along the rooftops, everywhere. So to implement sharpening, we actually have to change our kernel and actually use the cv2.filter 2D function. So the kernel for sharpening actually looks quite different here. However, as you can tell, it still sums to 1. And that way we normalize our image. Otherwise, if it didn't normalize to 1, your image would be brighter or darker, respectively. So let's run this simple sharpening example in our code. So again, we load our image and then we create our sharpening kernel. So as you saw before, we have -1s in all rows here and columns, except in the direct center where we have 9. So if you were to sum all the elements in this matrix, you'd actually get 1, which is exactly what we wanted, which means it's normalized. And to run or implement this sharpening function, we use cv2.filter 2D to implement the sharpening effect. So we take the sharpening kernel and the input image, we run it, and we get our sharpened image here. So let's take a look. And there we go. This is our original image, and this is our much sharpened image. And as you can see, just like the image we saw on the slide, all the edges are much more pronounced. Sort of looks a bit artificial, but you can play around with your kernel matrix and try your own sharpening matrix. There are ways to actually get a much nicer looking sharpened image here. Okay, so let's now talk about thresholding. And thresholding is actually a very important OpenCV function that is quite useful, and you'll find we use it in many of our mini projects going forward. So what exactly is thresholding? Thresholding is converting an image to its binary form. But what does that mean exactly? So if you look at the function, it's the cv2.threshold function, this gives you an idea of what to expect. So imagine we have the input image here, a threshold value, which is very important, a max value, and a threshold type. So I'm just going to quickly illustrate what happens in this function here. So let's look at this grayscale image here. And also please note, all threshold functions use grayscale images. So images need to be converted into grayscale before thresholding here. So this is a grayscale image. It goes all the way from 0 to 255 at the bottom here. And let's assume this is our midway point, 127. That's our threshold value. So, and max value here is a value we want to set everything above that threshold to. So in this example, if this line here is 127, everything above it, going to 255, becomes 255. So this portion here becomes white, and this portion above here becomes black, which is 0. So there's different forms of thresholds, which we'll see in the code, but that just illustrates exactly what's happening here. There's also a type of thresholding called adaptive thresholding, which we'll come to in the code as well. And you may have noticed I used the word binarization here. Binarization or thresholding refers to the same thing. It means we're converting a fully grayscale image into just 2 points, a max point and a low point. Traditionally, it's 0 for the low point and 255 for the max point, so white or black. Okay, so let's take a look at implementing some of those threshold methods that we just discussed. So as you can see, there's 5 different thresholding methods we're going to use here. There's binary, binary inverse, truncation, trash to 0, trash to 0 inverse. So let's run this code and we can actually figure out exactly what each is doing. Okay. Oh, just to know that I actually set the windows specifically here. It doesn't OpenCV isn't so nice to automatically lay out those windows. There are some CV2 move window functions that allow you to do that, but I'm not going to discuss that right now. So anyway, back to thresholding. So this is our original image here. And remember from the slides I said we set 127 to be the threshold value. So in threshold binary, everything that's below 127, which is our value we use in our code, hopefully you remember that, goes to black, and everything above that goes to white. So threshold binary inverse actually, and understandably, does the opposite, the inverse of that. So everything darker than 127 goes to white, and everything higher than 127 goes to black. Now, trash trunk does something a little bit different. What it does is that it takes everything that's actually brighter or higher than 127 going this way and caps it at 127, which is why everything just stops at this gray shade here and continues along this gray shade. So what about trash to 0? Trash to 0 actually does something of the opposite here. Everything that's actually below 127 actually gets capped to black, similarly to threshold binary here. However, it leaves everything above 127 alone. So it's a nice effect, can be useful sometimes. And trash to 0 inverse actually does the opposite now. So as you can see, it maintains this color here. This is the initial 0 to 127 part, but everything above 127, just like in threshold binary inverse, goes to black. So let's close these windows now, and we can actually just quickly look at the code. As you remember, the input image is the first parameter here. 127 is our threshold value. 255 is the max value we set. That's the value it goes to when it's above that threshold, or vice versa. 0 is actually used in the opposite case for most of these threshold algorithms. And this here, trash binary, this is where we defined the threshold type we want to use. So it's a simple 4-argument function, CV2 threshold. Hope you have fun using it. So you may have noted one weakness of these threshold algorithms is that they all require us to set the value at 127 or whatever value we wish to use. Now that's not that convenient when you're actually doing it with, like, say, scanned documents or anything of the sort. So is there a better way of doing this? And yes, there is. It's called adaptive thresholding. And I have a slide in our presentation. We'll discuss these methods here. But there's quite a few adaptive thresholding methods used in OpenCV. There's adaptive mean trash. There's Ostu's method, which is quite popular. And there's Gaussian Ostu's method. So let's run this code and we can actually see what's going on here. So this is the original image we're looking at. It's Charles Darwin, Origin of Species. So that's the original image. This here is a regular binary threshold that we previously used. As you can see, it's good. It's not bad. But if we wanted to get this text crisper, we would have had to use maybe a lower or higher value of 127. So this is it here with adaptive mean thresholding. As you can see, you can compare directly to this image and you can see the text is a lot more clearer. So without setting a threshold value of 127 or anything of the like, it actually does a better job already. So can OS2's method do a better job? Perhaps it can. I mean, there's not much difference separating these images, but in my experience, OS2's method actually is quite handy. What about OS2's Gaussian method? Again, this actually looks very similar. There aren't a lot of differences between these images here. However, in your own image dataset, you may want to actually play and try these different thresholding algorithms. So let's learn a bit more about the adaptive thresholding methods that we just saw. So the first one we saw was adaptive threshold. And as you remember, the adaptive thresholding has a big advantage in that it reduces the uncertainty in setting a threshold value. So the input, there's no threshold value in these parameters here. There's a max value, which is 255, the adaptive type, threshold type, block size, which needs to be in odd numbers, one of those where the OpenCV quirks, and a constant, another OpenCV quirk, that needs to be set at 5. Well, traditionally 5. You can experiment with different values, and if you get better results, that's good. So let's quickly look at our again. So these are the values here. So this is the adaptive type, and I believe this is the only type available for this function right now. And this is the thresholding type we use here as well. And these are the block size and the constant here. And that gave us the results we saw earlier. So let's go back to our presentation now. And I actually just misspoke when I just said adaptive thresh means C was the only adaptive threshold type we could use in this function. There's actually adaptive thresh Gaussian C, which, as you may remember, is the weighted sum of neighbored pixels under that Gaussian window. So let's discuss OS2, which is actually one of the best adaptive thresholding methods. So what OS2 does is that it tries to find, well, it looks at a histogram of the range of intensities in the image here, and it tries to find the peaks or the modes of the histogram here, and then it actually finds a value that separates these histograms, the best value that can separate these two histograms. That way you actually get the best thresholding value here. So in most cases where you have changes in light intensity, I would encourage you to use one of these adaptive thresholding algorithms. OS2 is actually quite good. However, if your application can use a simple thresholding algorithm that we saw before, those may be faster, so maybe you should just go for one of those. Again, it depends on the use case, and you'll see going forward we actually do use different thresholding methods in our mini projects. So let's explore dilation and erosion. These are two very important OpenCV operations and are quite useful in image processing. So the best way to explain this is by looking at examples here. So this is a letter S here. It's a white letter on a black background, which is what the zeros and ones correspond to. You can consider the ones to be 255 if you want, just to maintain the OpenCV standard. So let's look at what erosion does. Erosion removes pixels at the boundaries of an object of an image. What that means is that the boundaries of the object being the letter S here, imagine everything is gone here and on the boundaries itself. That's exactly what erosion does. So we get a thinned out letter S here. Dilation, however, does the opposite. Dilation adds pixels to the boundaries of an object here. So this is why the S becomes much thicker in our dilated segment here. So what about opening and closing here? Opening and closing are actually useful functions that combine the dilation and erosion together. So opening is erosion followed by dilation, and closing is the opposite, dilation followed by erosion. As you can imagine, an erosion followed by dilation would be very useful in getting rid of noise. So imagine if there were some little white specks in this image. If we erode those images and those become thinned out or disappear altogether, then we do a dilation, we actually preserve the initial image here that we want to maintain. So now, dilation and erosion, while simple, actually causes a lot of confusion with first-timers who try to use it, and it all because there's a false misconception about what it does. Now, yes, it does. Dilation does in fact add pixels to the boundaries of an object, and erosion does remove pixels to the boundaries of an object. However, imagine we have a black text on a white background. OpenCV interprets this white as being the object itself. So when we run an erosion here, it's actually going to erode into this here. So erosion is actually going to have the thickening effect of a dilation. And a dilation is going to have the opposite effect. It's going to have the thinning effect that you expect an erosion to have. because what's happening here is that the boundaries of the image are basically the inner points here. So when we dilate, we're actually making the white bigger on the edges of this O, P, and whatever else in OpenCV word here. So please don't get them confused. It happens quite often. It happened to me actually. So don't feel bad if it happens to you. So let's now look at implementing dilation, erosion, opening, and closing in our code. So the first thing to note is that we actually need to define a kernel, and we define it by using numpy's ones function, data type here, and we have a 5x5 kernel in our example here. So the erode function and dilate function both follow the same pattern here. We take the input image, the kernel size we defined here, and iterations, which is how many times you run it. In most cases, you would never need to run this more than once. However, if you do run it 2, 3, or whatever amount of times, you actually increase the effect. It's like running the erosion twice on the same image. So let's run this code and we'll take a look and see what happens. So this is the OpenCV text which I wrote out in Windows Paint. This is it eroded. As you can see, it has the effect that we anticipated. It actually erodes the boundaries here, making it much thinner. And let's see dilation now. Exactly as we anticipated. So as you can see, dilation adds pixels to the edges here. So it actually, everything appears much thicker, as if it was written with a marker and not a pen. And let's look at opening. Opening is the effect of erosion, then dilation. So as you can see here, because this, when we erode it, actually disappeared these boundaries here, when we dilate it now, it actually misses these things totally, because there is nothing to dilate on the side here. So that's why opening, so that's how opening has this effect on the image here. So let's look at closing now. Now, closing actually looks quite nice, and the reason for that is because closing is dilation first, then eroding. So what we did here actually should get us back something to our original image. And actually it does. If you look at it, it's actually pretty much the same, just barely noticeable. So these operations that we've just seen are actually called morphology operations, and there are actually a few more. You can take a look at this link to view the others on OpenCV's official documentation site. However, they aren't as useful as dilation and erosion in my opinion, but however, you may have a special use case for it, so feel free to check them out. So let's move on to edge detection and image gradients. So before we continue into this section, I want you to think about what exactly is an edge. You may define an edge as being the boundaries of images, and that actually is sort of right. As you can see in this little picture of a dog here, we can understand that this is a dog because the edges are drawn in. We have the edge of the tail, his body, his face, and his paws, so we know it's a dog. So as you can see, edges do preserve a lot of an image, even though a lot of the detail is missing here. So how do we formally define edges? Edges can be defined as sudden changes or discontinuities in an image. And this picture I've drawn here actually highlights this example. So imagine you're moving across this line here. And this is the intensity as we move along this line here. So as you can see, the intensity is high here. Then suddenly it gets low, which is what this trough represents. And then it gets high again. So this dip here represents an edge here. And vice versa, if this was a white line and a black background here and a black background here, we would have the opposite shape here. So that's how we actually define edges here, by finding the image gradients of the intensity changes across these lines here. So fortunately, OpenCV provides us with some very good edge detection algorithms. We're actually going to discuss 3 of the main ones here. That's Sobel, Laplacian, and Canny. Now, Canny is actually an excellent edge detection algorithm, and it's really good because it has a low error rate. It defines edges well, and it's actually very good at picking up edges here. This here is actually a very hard image here for edge detection algorithm to look at. It's of a dark dog, or Rottweiler actually. And as you can see, you can actually make out that it's a dog quite easily here. So I won't go into the details of all of these algorithms because they actually get quite mathematical. However, I'll just give a high-level explanation for Canny edge detection. So what Canny does, it first applies a Gaussian blurring effect to the image. As you previously saw, we did some Gaussian blurring a few chapters behind. And then what it does, it finds the intensity gradient across the image. Then it applies a non-maximum suppression, which is actually removing the pixels that aren't edges in the image. And then it applies some hysteresis thresholds. So if a pixel is within an upper or lower threshold, then it's considered an edge. And you can learn a bit more about canny edge detection and different edge detection techniques at these links here. So now let's look at implementing these edge detection algorithms in our code. So let's look at implementing some of those edge detection algorithms we just discussed. So the first one we're going to discuss is sawbell edges. And what's cool about sawbell edges is that we can extract vertical and horizontal, vice versa, edges from the image. I'm not going to go into the details of this function. Although this is kernel size, you can adjust this to get different strengths. And this is the input image here. And then we can actually combine both X and Y edges and using the bitwise OR and show them together. Laplacian is run here with CV2 Laplacian, and it's just there's no threshold or parameter settings. Laplacian is just a blanket function. And then there's canny, and canny is actually quite simple as well. It just takes two threshold values here. So let's run these edge detection algorithms and compare them. So this is our input image. Remember it. These are the horizontal edges in sawbell. These are the vertical edges in sawbell. These are them both combined. This is Laplacian, and as you can see, Laplacian actually identifies a lot of edges, but also a lot of false positives in the sky. So if only there was a way we can tune these thresholds to give us some nice edges. Maybe that's what canny is good for. As you can see, canny actually disregarded the sky and a lot of other excess noise, but actually preserved the edges that we wanted to see, which was in the structures. So what we can look at here is in canny is that we can adjust these two threshold parameters here. I've written up something quickly here. However, just note that these parameters here are gradient parameters. So let's set the gradient parameters that we want to look at to some tighter values. So let's say 50 and 120. Let's go over sawbell horizontal edges, quite nice, vertical edges, combined, Laplacian. There we go. So as you can see, the images looks a little different. It's not vastly different. However, you can play with your thresholds in canny and see if you get the best, whatever you want as the best edges to represent your image. Okay, so that's it for edge detection. We'll move on to some other stuff now. Let's take a step back and look at affine and non-affine transforms again. So imagine you have an image like this here, where this is clearly a non-affine transform of an original top-down flat image here. You can see the lines here, they're not parallel anymore, and they're actually going to join in some future spot, maybe somewhere up here or further up. So what that means here is that if we have the 4 points here, we can actually use an OpenCV function to actually warp this image here and get an image like this. So clearly we can take a skewed image once we're aware of the 4 points of the corner and get back the original image. So let's take a look at that, implementing that in some code. Okay, so let's look at implementing that perspective transform that we just saw. So remember, we firstly need the coordinates of the 4 corners in the original image. So that's what we actually have here. These are the 4 points here, and we're basically combining it into a points array here, comprised of these 4 coordinates. And then, so these are what we call points A. And then we have points B, which is the output, which is the points that let's go back to the image here. These are the points that we want to define here. So that's a typical A4 standard page size. We need to give it that so that it actually knows what to transform it to. So what we do now, we actually use these 2 points, these 2 sets of points here, with this OpenCV function called getPerspectiveTransform. What this does, it actually generates a matrix, and this matrix here is basically the transform that basically transforms points A to points B. And then we use warp perspective, that function you may have seen previously, to actually generate the output, to use this matrix here and generate the output image, which we've called warped here. And this here is the final size of the image we want to see. So as you can see, it actually lines up with this here. These were the 4 coordinates of the output image that we wanted. So let's run this code. And voila, we get the actual warped page here. If you wanted to do something smarter, you'd probably write an algorithm that gets the contour of this image, then automatically gets the locations of the corner points, then feeds it in, and then we run everything automatically. It's actually not too hard to build. There's actually some blogs online that actually do it for you. So we've just seen how we generated a matrix for a non-affine transform. But what about an affine transform? That should be simpler, right? And indeed it is. You only need 3 coordinates to actually generate a affine transform. So similarly, we have points A and B. We actually use a different image here, and there's a reason for that. I'll show you shortly. So we have 3 coordinates for points A and B, 3 coordinates for points B. We use get affine transform as opposed to get perspective transform. And we similarly implement those transforms using warp affine. We just switch this here with column and rows, which is similar to using the actual dimensions here. We just take it directly from the image. And let's run this code here. So as you can see, these are the shapes that we wish to transform. So let's press any key and continue. And this is the affine transform. As you can see, this affine transform actually rotated the image slightly, didn't adjust scale or anything, but as you can see clearly, all the lines maintain their parallelism here. So that's one of the main points of affine transforms. So I hope you get a feel of using these functions here. They're actually quite handy and quite important when we're doing more complicated stuff in OpenCV. Hi, okay, so you've made it to our first mini project. This is using our webcam to create a live sketch of yourself. So let's quickly run this app and see what it does. So this is me here talking in my bedroom here. This is me waving around. And this is me here with my cell phone being charged at the moment. So you can actually see the code. It's quite cool. So this is our sketch app. It works pretty well, generally. I mean, you can play with the parameters in our app to get it better better to your taste. So let's see exactly how this is implemented. Okay, so here's the code for our live sketcher app. It's fairly basic, although we do introduce some new concepts here. And the first thing we introduce here is creating a function, an OpenCV or image processing function called sketch here. If you're unfamiliar with functions, imagine a function being basically a group of commands here that we call when we run the sketch command over here. So sketch actually does a bunch of processes here and returns an image for us. So it actually combines multiple layers of image processing and just returns the final output. So it's pretty cool. The second thing I want to introduce you to is actually using the webcam. Now using a webcam in OpenCV is actually quite simple. What we do here, we actually run this initializing video capture function here, and it basically creates an object called cap. Cap here can be read now, which is cap.read here, and what that does, that pulls an image from the webcam. However, if you run it out of a loop, it just pulls the image at a time and nothing else. So what you want to do is have cap.read running in a loop, and this loop runs continuously, pulling images from your webcam. It should be pulling at the frame rate of your webcam, which is usually 30 frames a second. Sometimes it's more, sometimes it's less, but generally it's either between 24 and 60. And cap.read also returns ret. Ret is basically just a boolean that defines true or false whether this was run successfully. However, the real meat of this cap.read function is frame. Frame is the actual image captured from your webcam, and frame is what we pass to our sketch function here. And lastly, this little 2 lines of code here basically tells us that the loop only breaks when we press the enter key. So cv2.wait key previously was at 0 before, took any key in. I'm just introducing now, we can actually define a wait for special commands. So in this case, when you press the enter key or return key, it breaks this loop. One other important thing to remember when using a webcam is that we need to do cap.release. Otherwise, again, what happens in OpenCV is that it hangs and actually locks up your terminal, and you have to go to kernel restart to run it again. Okay, so let's take a look at our function here. We defined as sketch. This is actually doing the bulk of the work, and it's where we keep all the image processing OpenCV stuff here. And it's actually a very simple function. So let's take a look here. So what it does, we take the frame from our webcam here, pass it to sketch. We then convert it into a grayscale image, and then we apply a Gaussian blur to that image here. The Gaussian blur is basically to just smoothen and clean up any noise in the image, because webcams aren't very high quality in most cases, so they do produce a lot of noise. So once that image is blurred, we pass it to a canny. As you remember, canny was our edge detection algorithm, and these are the thresholds we set here. These thresholds, please feel free to edit and play with them as you see fit. They can give you different results in different lighting conditions. These are what I found optimal to my taste and my lighting conditions, but you may find something different. And once we have canny, you remember canny was a black background with white edges. However, I was trying to illustrate more of like a pencil on paper type thing, so which is why I used Tresh binary inverse to invert and threshold the canny edges here. Now we could have also used some of other inverse functions here, and you may remember we could have used a bitwise knot to invert. However, the reason I use this threshold function here is so that we can actually play with this parameter here. This was our threshold parameter, so it gives you some more flexibility here. And what this does here, this creates a mask, and then this function returns our mask back here. So this actual block of code here actually is a variable itself that's returned from the sketch function, which is how we can show it with the imShow function. So that's basically our live sketching app. Something very simple and something you can actually play with on your own. Feel free to actually add more effects as you see fit. Thanks. Hi, and welcome to section 4, where you're going to learn about a very important topic in computer vision, and that topic is image segmentation. So what exactly is image segmentation? So simply put, image segmentation is a process by which we partition images into different regions. So here we have a few simple examples. So looking at this Volkswagen Beetle sketch here, we can see using an image segmentation technique called contours, we've actually extracted all the body parts, so all the major body parts of the car. Maybe we've gone a little overboard in some areas, but overall it's quite nice. And looking at the domino over here, we can see every bounded region in this little domino sketch has been extracted by our image segmentation technique. And moving on to some handwritten digits, we can see every number here has been isolated by our image segmentation technique, as well as in this bottle cap collection. We've identified the circles quite nicely here. So in this section, we're covering quite a few image segmentation techniques, starting first with the very important contours. Contours form a very important segmentation technique in OpenCV, so it's worthwhile we spend some time doing it. It leads us to a second mini project where we identify shapes by contours. We then look at line, circle, and blob detection, which are all pretty important as well, and that leads to our third project where we're actually counting the circles and ellipses in an image. So let's introduce our first image segmentation technique, and that's contours. So contours are the continuous lines or curves that bound or cover the full boundary of an object in an image. So this picture here illustrates this concept quite nicely. Here we have a piece of paper on a black background, the paper being the object in our image, and the green lines being our contours. So these green lines here cover this paper totally in this image. So this is a very good illustration of what a contour is. And in case you're wondering why we actually bother to find contours, well, contours are extensively used in object detection and shape analysis. Okay, so let's begin implementing contours using OpenCV. So let's load our Understanding Contours IPython notebook file here. It's lecture 4.1, and it brings up the file right here. So this is the code for our first contours project. Seems slightly lengthy, however I'll step through each line to make sure you get a good grasp of contours. So let's load an image of 3 black squares here on a white background, which we'll see shortly. The second part of the program you may notice is that we grayscale the image here. Now grayscaling is a key step when you're finding contours, mainly because the OpenCV2 find contours function here can only process grayscale images. If you were to pass a color image here, it would actually return an error. So the next set of image processing we do is finding canny edges. Now finding canny edges of the image isn't necessary. However, I find in practice it reduces a lot of the noise that we experience when we're finding contours using the CV2 find contours function. So this is something you can play by ear, maybe experiment with it or not. Just keep it in mind that it actually can help reduce the number of unnecessary contours when using find contours. Okay, so let's move on to our find contours function here. This is the main core of this program. So this function, cv2.findContours, takes 3 input arguments. It takes the input image here, which is our canny edged image. It takes the retrieval mode and the approximation mode. And there are several options in each of these here, which we will discuss shortly. After which, we display our edged image. And the reason I displayed for is that I wanted to tell you, or I should tell you, that FindContours actually edits this image. If you don't want to edit your image, use this instead here, edge.copy. .copy is a Python function that actually copies this image here, or the variable here. So we don't actually edit the original variable. So moving back to the outputs of FindContours, it returns the contours, which I'll explain shortly, and the hierarchy. And later on we print number of contours found in our image, and then we draw the contours on our image. So if you remember in our drawing functions, it takes the input image, it takes the contours, which are points, and I'll explain that again shortly. Then this -1 here tells it to draw either all contours, or we can actually index it to draw the first contour, and delete a comma there, or second contour, and vice versa. So let's keep it at -1 to draw all. This here is the color, and I believe this will be green, PGR, yes. And this is the line thickness here. So let's run this code and see what's actually happening here. Here we have our 3 black squares. These are the canny edges, done very well. This is exactly how FindContours edits the image. It does some sort of overlay with the contours, so this is why it looks like this. You probably won't ever need to use this image, so but keep that in mind if you're ever playing with your FindContours function. All right, so let's actually see the contours now. So this is perfectly done. These are 3 contours that have properly segmented our black squares here. So you've just ran your first contour extraction code. And as you can see here, it actually outputted that we've created or found 3 contours, which is exactly as we saw. So now let's do some other interesting things with contours. Let's take a look at the actual contour file. So let's actually print the contour file here that we extract. So let's do print contours. Let's run our code. There we go. So here we have a matrix, or it looks like coordinate points, XY points of contours. So what exactly are we doing here? So OpenCV stores contours as a list of lists. And what a list of lists is that, remember when we ran the length function on our contour file, we saw length being 3. That means there are 3 lists of lists in that file. So imagine contour 1 being the first element in that array, and that element contains a list of all the coordinates, and these coordinates here are the points along the contour. Now there are different ways we can store these points, and that's called the approximation methods, which we'll come to shortly. Okay, so let's head back to our code and I'll teach you a bit about approximation types. So as you saw here, when we printed our contour file, we saw a bunch of points here. So these points are actually the points that lie around the contours that we just saw, those green squares or rectangles around our blocks. So let's look at the notes here on approximation methods. Now there are 2 approximation methods here. There's chain_approx none and chain_approx simple. Now difference between these two is that chain_approx none actually stores or gives you back all the points along those green lines there. So it's going to be a ton, or an exorbitant number of points. However, chain_approx simple actually gives you the bounding or the endpoints. So it gives you basically like a polygon. So if it's a square, it's actually just going to give you 4 points. If it's a triangle, 3 points. So this is a much more efficient way of storing contour points. So just keep that in mind if you're finding contours in large images or large sets of images. So we're going to talk about retrieval mode. Okay, so let's actually take a look at retrieval modes now. And retrieval modes are sometimes a bit confusing. Actually, to me, I found it a bit confusing the first time I looked at it. However, they're actually not that confusing, and they're basically just 2 main types that you'll be using in most cases. So let's take a look at the types here in our PowerPoint slide. So retrieval mode essentially defines the hierarchy of the contours. So hierarchy being like, do you want sub-contours, or do you want external contours, or do you want all contours? So let's look at the 4 types of retrieval modes here. There's retrieve mode less, which returns all contours, which is good if you just want everything. there's the retrieve external, which gives us only the external contours, and I actually find this to be probably the most useful one in most cases. However, there will be times you'd want a contour that's within a contour. Imagine like a donut shape, perhaps. There's retrieve comp and retrieve tree. Retrieve tree is actually also very useful as well. I said the first two are most useful, however, tree is actually very useful. Tree returns, I'll tell you why. Tree returns the full hierarchy information of that. Now, hierarchy information is a bit confusing, and I'm not going to discuss it in length here unless you guys wish for me to do it. I think in most cases you don't necessarily need to understand them too much, but if you want, you can click this link here and actually get a very detailed tutorial on hierarchy modes here. So just to simply illustrate something here, by setting the different retrieval modes, our hierarchy file, because if you remember correctly, let's look at the code again, define contours function returns contours and hierarchy. And if you were to look at hierarchy, hierarchy would actually give you this contour, the present layer, I guess you can consider it like a layer, the next layer, and the first child and the parent. So these are a bit confusing, so I suggest you read this just to get some more information here. Okay, so let's go back to our code and illustrate the difference between the first two contour types. Retrieve list, which retrieves all, and retrieve external, which retrieves the outer contours only. Okay, so let's take a recap at what this did here. So we see we've got the contours there. So let's change our file now to another file here in our directory called donut. It's a square donut because it's a donut shaped square. Sorry for the bad terminology. So that's our donut shaped square on the left. As we can see, we've got the three external contours, but the contour inside has been totally ignored. So now let's change this now to list. Sorry. Let's run this code again. And there we go. So we see now list retrieves all contours, including the inner contour in this square. So that's a good example of how their different retrieve modes work. So when you're implementing some projects later on, please always consider whether you need to get external contours only or whether you need to get all contours. And in future, if you do want to extract inner or outer contours only, you can use functions like retrieve all or retrieve list, and actually use hierarchy to actually identify different layers or levels of contours, which is quite cool. So that concludes our gentle introduction to contours here. Let's now look at sorting contours. We can sort from left to right, or we can sort by size. So that's pretty cool. So let's take a look at that. So let's talk a bit about sorting contours. This is a surprisingly useful technique when applying object recognition algorithms or machine learning classification algorithms. Sorting contours by area, which is the first technique we discuss, helps us eliminate small contours which may be picked up as noise, or extract the largest contours, which may be the most important parts of the image we wish to analyze. Furthermore, sorting by spatial position allows us to sort characters. Suppose you're looking at handwritten text. It allows us to sort characters left to right, which is exactly like how our brain processes it. So now let's take a look at these sorting algorithms I've developed in the code. Okay, so let's open lecture 4.2, sorting contours, in our IPython notebook. Okay, so we see some code here. So before we actually begin explaining this code, I invite you to run this code. So let's run it together. So these are our four shapes here: square, triangle, small square, and circle. These are the canny edges that we extract from that original image. These are the contours, and this is something new I wanted to show you guys. What I've done here, I've taken the contours from the original image and drawn them over a black background. This way we can actually, this is a good technique in actually looking at contours separately from the original image. And these are the contours overlaid on the original image. This would be helpful in case, like, imagine we had a green image here and you didn't know if the contours were drawn correctly. That's why we do this. At least that's why I do this occasionally, so I can see the visibility of my contours quite clearly. Okay, so let's close this and then we'll begin sorting. So if you're curious as to how I created a blank or black background image, I simply use numpy zeros function here and use the same dimensions from our original shape, and then put the 3 layers for the RGB colors here and call this black image. And then we draw this over here, draw contours over our blank image. So this is the contours file that we extracted previously, and that's simply it there. Okay, so let's scroll down now to see how we actually sort by contour area size. Okay, so before we begin going through this code, let's just run this code and see what happens. So this is the largest contour here, square, and it's highlighted first, then the circle, then the triangle, then the square, the smaller square. So we can clearly see we're sorting by size here. So let's see how we do this now. So firstly, one thing you should note in IPython notebooks is that we actually defined or found our contours here in this previous cell. However, we can reuse that contour file here. We don't need to actually run that line again using IPython notebooks. Everything, all the variables that exist here are also available to use here. So that's something you should keep in mind. So let's actually see how we sorted by contour size. So you can see we printed here the sizes of the contours here. This is the unsorted size, and this is after sorting, and you can see it's in largest to smallest here. So how did we do that? That's done by this line here. This is sorted as an OpenCV, sorry, it's a Python function that takes into consideration, this is the contours that we're sorting. This is the function that we're passing the contours to. So we're passing every element in the cell to this function here. And this is the order. Reverse equal true means we're sorting from large to small. False means we're going from small to large. So contour area is an actual OpenCV function, and we use it here. In this function I define up here. This function simply takes the contours that we created up here, and what it does, it loops through each contour in that contour file, and it calculates the area of that contour. That's what cv2.contourArea does. It calculates the pixel areas, sorry, the area of the contours in pixels for each contour. And then we return this array here, this array called all areas here, and that's what we print here. So we printed it before and after sorting. And then, as you can see, we step through or loop through each contour by size. That's done in this 4 lines right here. So we've saved our sorted contours as sorted contours, quite nicely named. And for each contour in the sorted contours, we're drawing the contour over our original image. This is the contour we're accessing here. -1 again saying that we're drawing all contours, even though in each case it's one contour we're looping through here at a time. The wait key allows us to step through key by key so we can see the contours by area, and then we're showing it here. So that's basically how we sort by area. We're now going to move on to how we sort contours by left to right, which is a bit more involved. However, it's quite simple as well. Okay, so let's move on to sorting contours from left to right. Now this code is a bit more involved. However, it's actually not too difficult to understand as well. So these are some functions I define here. We'll get into that shortly. So we load our image and make a copy of our image here. And then we use this here to run basically a labeling function on our contours. Again, I'll get into that shortly. And basically this is again, we sorted here by our own function. Remember previously we sorted by using OpenCV's contour area. We've now defined a function called x coordinate contour. As you can imagine, this sorts by the order of the x coordinates. Hopefully that was self-explanatory to you. And then we run a loop here. This is a loop where we actually label our contours left to right. And in case you're wondering what enumerate means, enumerate basically allows you to count this variable here, I. So every time the loop runs, so every time it's going through 4C in contours itself here, it's incrementing I. And we use that to actually plot or actually count or label the order of the images here. And there's something else going on here which I'll describe shortly. It's about cropping contours. So there's a lot going on in this code. So let's quickly run it and maybe you'll get a better idea what's happening here. Okay, so let's quickly discuss our first key function here, and that's the x coordinate or xcoord contour. What this function does, it returns the x coordinate of our contour centroid. Now centroids, we haven't actually dealt with that yet, but what centroids are, basically we use this OpenCV function called cv2.moments, and what it does, is that it takes the contour in question here, and it actually returns the center point of it. So later on here, in this other function here, you can see we have moments, C, which is our contour in question for this function here, and Cx and Cy, based on the moments here that we calculate here, this is roughly the center point or center of mass. You may have heard that term in physics before. So this is the center of mass of the contour, the x position and the y position here. So once we extract the x position here, that's what this line is here. As you can see, it's the same code as this line here. That gives us the x position. So that's how we can actually sort using the sorted function here in Python. So what this does here is that this returns the x position for each contour that's been inputted here. And we sort from smallest to largest here. Mainly because we're going left to right. As you remember, OpenCV has a top left corner from 0 position. So going from left to right is basically small to large. Okay, so the other parts of the code that may be interesting is, firstly, let's see how we labeled the center of masses or on the contours itself. So what we do here, this function I created here, takes the image, takes a contour. Actually, we don't use I anymore, so you can actually delete I. It doesn't actually do anything. And you can delete it here as well. So it's a redundant thing. Maybe I was editing the code previously. So anyway, what this does, it takes the image and the contours, and it actually draws a circle at the center of mass for each shape here. Then it returns the image back to it right here. So that's what this does here, and it edits the original image here, and we have the centers highlighted in each of the image. So let's take a look at that again. There we go. And then we label it left to right, right here. Okay, so now let's look at the third key important part of the code here, which we've done the labeling and stepping through before previously, so you should have a faint idea of at least what's going on here. If you don't, I can quickly go through. What's happening here is that we're plotting the label according to the order here. Label being I. What we're doing here is actually looping through the contours here, and again we're doing this enumerate type loop, which we've seen. Actually, we haven't seen it before, so this is the first time we're actually seeing it here. So what enumerate does, it loops through this contour file here, and what it does though, it actually iterates I each time it actually loops. So we're using I to be basically the order. So I plus 1, because I starts at 0 unfortunately. So we add 1 here. So using the put text function here, we're putting text here at the center point of the image here. So let's take a look at that again. So we see the center points previously drawn here. That's what we highlighted before. And now instead, we're actually putting digits using put text at the center of each contour. Now you can see it's not directly, the labels don't always come up in the direct center. That's because the point is here, but put text generates the image. Basically, I think it's at the top right of that point. So that's what's going on here. The second part of this code here, this loop I should say, that's interesting, is that we're now cropping our contours. Cropping our contours is something we didn't discuss before, but it's actually very useful, especially when you're feeding it to a classifier. So how we're doing that is that we're actually using this OpenCV function here called bounding rectangle. And what that does, it actually gives you the rectangular overlay of a contour. So in a square and rectangle, it's the contour itself. However, in a triangle, it actually is the square block at the extreme points of the rectangle. So by using bounding rectangle, we extract the four extreme points, x, y, w, h, and I'll discuss a bit what that means secondly. Actually, I'll do it right now, so you get an idea of what's going on. X and y are basically the starting points of the first contour. So imagine you have a square, and you have a top left starting point here, where this mouse cursor is. Hopefully you can see it. And width and height are basically the width here that extends this way, and the height that extends down over here. So that's actually how we get the bounding rectangle here generated. And using NumPy, which we previously saw, we can actually crop images here. So we're going from y to y plus h, and the reason it's plus h for is because I said it gives you the height and the width of the image here. It doesn't actually give you the endpoint, the actual coordinates. It gives you the length of pixels. It goes in that direction. So it has to be y plus h, and x has to be x plus w. And what happens here is that we're actually cropping the image here, and we're creating a file name here called image name. So we're concatenating some data here to be a string. So it's output shape underscore the string name, well, the string number converted to a string, I should say, and the file end type here. And we're just printing it every time it goes here, so we know we've stored 4 images here in that file. And I'll actually open those files for you shortly. because what we're doing next is actually writing those files to our hard drive. The reason I have this here for is actually this is extracted from another project where I was writing files to the hard drive and then using those files to input into a classifier for object detection. So we can just quickly look at those files now. Here they are. This is the square. Whoops. They're a triangle. As you can see, it doesn't actually crop because you can't actually do a diagonal crop. So you have to do crops in rectangular form. The square and then the circle here. So again, you can see there's some white space here, which we can't get rid of because cropping is unfortunately a square operation. Okay, so that's it for sorting by spatial position, well, X position here. Similarly, you can sort by top-down position by actually using the Y values here. This will give you the positions going from top to bottom, or reverse it if you want in this loop. You can set it at true here and go in opposite order. So have fun sorting your contours. So what we're going to look at now is called approximating contours. So firstly, let's open this file here. This is 4.3, lecture 4.3 here. And let's actually run this code to see what's going on. So I have a very crudely drawn house that I did by hand in Windows Paint. Thank you very much. And this is what happens when we extract contours and use the bounding rectangle for our contours. So you can see we have a bounding rectangle for the entire house, then one for the roof. So I'm guessing found contours of this triangle here, then the door, and then the bottom half of the house here. So that's pretty cool. Now the contour approx function is what we're going to look at now. And what that does, it actually, as you can see here, tries to approximate our contour shape better. So this may look a lot similar to the actual initial contour operation here. However, what it does, it actually tries to approximate a polygon to it here. So let's take a look at the function here. So you can see in our loop here, we're looping through the contours again. We found fine contours right here, and we're finding all contours and doing no approximation here. Maybe I should have done simple approximation, although it wouldn't have made much of a difference in this example here. So going back to our approximate poly dp function here in CV2. This is how we approximate contours. It's actually very useful if you have a noisy image with jagged contours and you know a shape is supposed to be a square or a triangle. However, you're getting maybe multiple edges in that polygon. This function actually basically approximates it for you. So let's look at the parameters it takes in here. So at a high level, I'll describe exactly what this function is doing. So it takes three parameters into consideration here. It takes our input contour, something called our approximation accuracy, which I'll discuss shortly, and basically whether we want a closed polygon or an open polygon. Closed being preferred in pretty much all cases, I believe. So let's take a look at approximation accuracy. Approximation accuracy is basically how detailed or how finely grained do you want the approximation to be. If you want a low accuracy, and a good rule of thumb here is 5% of the contour perimeter. However, if you go too high, I should say, with accuracy, let's look at, say, using 0.1 here. Let's see what happens. It actually does something pretty weird. It actually tries to approximate the house into the frame of the house into a triangle. That's clearly not good. So what about if we use 0.01? As you can see, it actually tries to match the house even closer. So what I suggest is that you maybe play with these values a bit. 0.3 actually works fairly well in this case here. Basically, the lower the accuracy or the ratio to perimeter, the more precise the approximation is going to be. And the higher this value here, the more larger grain that the approximation is going to be. So just keep that in mind when you're actually playing with this accuracy parameter here. Okay, so let's move on to the convex hull. And the convex hull is an interesting concept, and let's actually run the code to illustrate this. So as you can see, we have our hand here, sort of like a blurred hand right now. And continuing, we have what's called the convex hull. Now the convex hull, basically, if you can kind of figure it out from this image here, it looks at the outer edges here, and it draws lines to each edges here. Basically, it's what you call the smallest polygon that can fit around the object itself. And how it's found, it actually is pretty simple as well. So all that's happening here is that in this loop here, we're taking the contours that we found here. There's actually 2 lines of code I'll explain shortly here. It's not too critical, just something I just added in just to show you guys. And using the CV2 convex hull function, we generate a hull data type here, which is actually an array. And then we put this array into this draw contours, which takes in list function, a list variable I should say. And we just draw it over the contour itself, the image. So that's all there is to it in convex hull. It's actually quite simple to implement and use. This other line of code is actually, when you use retrieve list method, what happens is that without this line, let's just keep this, whoops, undo that. Let's just keep this here the same. So let's run the code again, and you'll see a box drawn over this image here. And what happens is that every time you find a contour on a white image here, it actually identifies the white background itself as a contour. If it was a black image, it wouldn't have happened in this way. So to get rid of that, which happens, what I tend to do sometimes is just use this little 2 lines of code here. That just, if I wanted all contours, but I wanted to eliminate that largest contour, I sort the contours by area, and I just use NumPy to index it I want everything except the first or largest contour. And that's simply what I do here. So this is a way to get rid of that first box around the entire image and generate just the contour that we want to look at here. Okay, so let's open up lecture 4.4, which is matching contours by shape. So let's open it here. Already have it open. So shape matching. Shape matching is actually a pretty cool technique implemented in OpenCV. So the code here looks a little bit confusing, but it's actually quite simple. So let's run the code and see what's going on firstly. So we have, this is the shape here, the template image that we're trying to find in another image. And here we go. So this is the image we're trying to find it here in. And we have identified that this shape here is the most similar to this shape here, at least according to our algorithm. And there are different methods of doing the shape approximations, or shape matching I should say. So this one here works pretty well. It actually found the closest match. So now let's see what's going on in the code here. So as I said, we load our template image in here. That's our 4-pronged star, and that's called our template image. And then we actually load our target image here, which is the file called shapes to match, or maybe you can consider it to be matched to. Alright, and then what we do next is actually first we threshold those images here. That's part of the procedure that we use in this in this code here. And then after that, we find contours in the first template image. So we extract our contours in the first image. Then we sort the contours from largest to smallest, just in case there were any noisy contours or discrepancies, because we do know we only want the largest contour. And next, since we have sorted our contours in order from largest to smallest, we actually remember previously when there's a white background, the first contour is always the big box, the big white box of the image, the frame. You can consider it. So we actually have to get a second largest contour here. So we extract this contour now. And then what we do, we actually again find contours now in our target image, which was a shapes to be matched to, I should say. So we do that here. And then, okay. So then we actually now loop through our contours in our target image. And this is where we actually use CV2's match shapes function. So what we do here, this is our template contour. Template contour was actually what we found previously, right here. And C is the contours in the other contour file. So remember the target file has multiple contours. There are multiple shapes in that file. So that's why we're looping through each of the contours in that file here. And these parameters here, which are different method and method parameters, these are, first method describes the contour matching type, which we'll get into in a moment. And then this parameter here, which is just basically a default parameter, don't interfere with it. There's probably going to be some work, since OpenCV is an open source project, there's probably going to be some work being done on this algorithm, but for now it's not utilized totally. So just leave it as 0, and it's actually a float 0 apparently. So what this function returns here is a match value, and basically lower means a closer match to the original image. If we were matching the exact contours, like exact same scale and size and order, the match would be basically 0. However, in this case, we're looking for the closest match. So we can try different match methods here, which I'll get into in 1 second. So after we print the match value here, what we do here is that just by trial and error, I figured out that anything that's under this value of 0.15 is going to be the closest match, or the match that's closest to the star shape on the other image. So that's how we determine whether it's a match or not. And if it is a match, we make that contour that we're examining in this loop here equal to the closest contour match. Otherwise, closest contour is a null array here. And then once that's done, we actually draw the closest contour using draw contours and output it. So that's pretty much how this code works here. So let's run it one more time. See our star, and this is the contour that closest match the contour of the star. So remember I said there are actually different matching methods here, this being the third parameter in this match value, in this match shapes function. So if you go to OpenCV's documentation here, which I'll put a link in our file actually just for safekeeping, and make this a markdown document for you guys. There we go. So if you look at this here, there are actually 3 methods here. There's contours match I1, I2, and I3, and this is the mathematics behind it, what's going on here. So feel free to experiment with it. We can just try changing it to 2 here and see what happens. It does work, but you can see the values here are indeed different. In fact, they're pretty much all under 1.5 here. So we actually pretty much got lucky, because the last one here was actually the match, essentially. And that's why closest contour was equal to C. So you can play with this and see, try different values. That happened again here. So yeah, so that's how we match contour shape using this match shapes function in OpenCV. Alright, so we've reached the second mini project here, shape matching. So what we're going to do, we're going to take an input image that looks like this here with 5 different images, and we're going to identify each shape, put the name of the shape inside of the shape here, and as well change the color of each shape. So let's get started. Okay, so let's get started with opening the code for second mini project. That's lecture 4.5. Let's bring it up here. Okay, so I'll just tell you beforehand, even though the code looks a bit lengthy and maybe a bit confusing, it's actually quite simple. So let's run the code first and get an idea of what's going on here. So these are our input image here with our shapes, unlabeled and everything black and white. There we go, stepping through one by one. Here's a star, here's a circle, triangle, rectangle, and a square. Cool, so let's see how it's done. So firstly, what we do, we load our image in here. As you can see, when we brought up the input image here, it was just a black and white image here. So there's no real need to threshold. I just have thresholding here because it's actually become maybe a bad habit now. But the most important thing to do is actually to grayscale the image here. So loading our image here into our find contours function, we use these parameters here, train approximate none, retrieve list, which gives us all our contours, and we get extract our contours here. So stepping through our contours here, do you remember this function, approximate polydp? Well, what we're doing here, just in case there are any edges or any other vertices that are considered when we're finding contours, which happens quite often, use approximate contours to get the approximate shape. So these are parameters that are fine-tuned for it here. However, feel free to adjust this as you see fit. So we have our approximate value here, the approximate contours here, sorry. So what we're doing now, we're checking the length of each approximate contour. If it's 3, because that's our approximated contour shape, then we obviously know a 3-sided shape, or sorry, a shape with 3 vertices is a triangle. That took a while to say. So then we actually draw now our contour. This is CNT here. We draw it over the image, and then using the moments, this is just done so we can actually place our text in the image here. And we've done this before, but you may have noticed I put -50 here. And the reason I put -50 on the x-axis here is because since it starts at the bottom right or bottom left corner, the put text here, I just wanted to pull back the text a bit more That way, this way this text stays in the image. Without this, and maybe I can demonstrate it for you if you want, but without putting the -50 here, the text was sort of like skewed across the image, and it didn't look too nice. And this is the font, the color we're using, which is black, and thickness and font size. So there we go. So that's how we identify if it's a triangle here. So pretty simple so far. Hopefully you're following me well. So what about if it's a four-sided shape? Here's where it gets a bit more complicated. Only because now that we have a four-sided shape, it can either be a square or a rectangle. So again, doing the moments and getting the moments first just to get the labels done, right? We find actually the bounding rectangle here. Now the bounding rectangle was done so that we can determine if the four-sided shape we have found here is a square or a rectangle. So how do we do that? So what we do, we basically just compare the width minus the height. As you remember, when you use bounding rectangle, width and height are basically the pixels it extends from the XY point. So imagine the mouse cursor being the XY point top left here. Width is in this direction, height is in this direction. If it's a square, those values should be roughly similar. So I have here, if the absolute value of w minus h is less than or equal to 3, then it can be classified as a square. And we draw it again. This is the color we're actually filling. Remember, -1 is to fill the image, the contour. This is the color we're using here. And we're putting the text in the center again. So now let's move on to star. Now when you actually run the star through it, you realize there's actually 5 vertices in a star. And that's pretty much how we identify the star, similar to the triangle. And again, circle basically we just said anything that's more than 15 vertices will be a circle. Now this could have been set at 11, 12. I just have it set at 15, mainly because in case we actually got more points on a star, maybe because I was tuning this beforehand, maybe this should have been set to 11, but it doesn't matter right now because it's still identifying this as a circle. Because as you can imagine, even with unless we do some very non-granular approximation, a circle is going to have a lot more points than 15. So there we go. So let's run this one more time. And we have labeled all our images correctly here. So congratulations, you've completed your second mini project. Hopefully you learned a lot by using this project. So let's talk a bit about line detection. Line detection is a very important computer vision method, and you can imagine it being used in applications such as lane detection for self-driving cars, or perhaps for something that actually detects lines on a chessboard, like this example here. So the two algorithms that are available in OpenCV are Hoflines and probabilistic Hoflines. Now there are some differences between them, which I'll illustrate when we run the code, but for now I'll just talk about how Hoflines represents lines quickly. I won't go into too much detail with the math, but you may have remembered this from high school mathematics, that you can represent a straight line by this equation, y equal mx plus c, with m being the gradient or slope of the line, and c being the y-intercept. However, in Hoflines, we represent lines a little bit differently. So remember, OpenCV uses here as its reference point, top left corner. So what we do here in this representation, we have p, which is a perpendicular distance of a line from the origin. In this case, it's pixels. And theta being the angle of this line here, normal of the line meeting this origin point here. And theta is measured in radians in OpenCV. So if you actually do open this theta value in OpenCV or access it, you'll see it's in radians. So these are some details here that I won't go into until we reach into the code, but this is basically the CV2 Hoflines function and the CV2 probabilistic Hoflines function. So let's actually use these methods now in our code. Okay, so let's open our line detection code here. That's lecture 4.6. Okay, so here we go. So firstly, let's run this code, give you an idea what's going on. So this was a blank Sudoku board here, where we had the lines here. So as we can see, we've actually identified all the major lines here. However, we've actually left out one line here, surprisingly, and we've identified multiple lines in a few locations here. You can see there's maybe 2 lines here, 2 lines here. This one looks like 3 because there's a ticker point here. So you can see it's not perfect, and what researchers do, let me just bring it up again, they sometimes merge these lines together. They find the average of the 3 closest points and merge them together. So let's take a look and see what's going on here. So similarly in the find contours function, we've grayscaled our image. We've found the canny edges, because canny edges helps quite a bit, especially in half-line transforms. Not transforms, sorry, just half-lines. And these are the parameters here. So these parameters here in this half-lines function, it takes the input image here, and then we set some accuracy parameters here. So the first parameter we set is the RAW or P value here. We typically set this at 1 pixel, but you can experiment with larger values if you wish. And then we set the theta accuracy to pi over 180 using numpy.pi or np.pi to generate our pi value here. And then this value here, this here is a key parameter. This is a threshold for determining if something is a line. So if we set this at a lower value, let's say at 150, we should get a lot more lines, way too much lines here. And if we set this at a higher value, let's say 300, we get only some few lines. So 240 was a good parameter to use for this. We missed 2 lines here, miscounted this one here. And that's the first part of the function there. So the next part of the code looks a bit confusing, but what's important to remember here is that CV2 half-line generates this object here, lines, and lines has row and theta values inside of it. So what's going on here is that we're actually looping through all the values inside of lines here and converting it into a format where we can actually get the endpoints of lines. That's how we use CV2.line, which we went through in section 2, I believe, and we just plot all the lines that this CV2 half-lines function generates. So now let's take a look at probabilistic half-lines, which is a little bit different, and actually the code looks a lot shorter, and that's mainly because we don't need to convert it into a format, the line format into something that CV2.line can use. It actually generates our start and end points of lines automatically here, and also has similar parameters here where we have pixel accuracy, theta accuracy, but it also has some new thresholds here. There's a minimum line length and a maximum line gap, as well as a threshold value. And similarly, we do have to grayscale and use canny edges again. So now let's run the probabilistic half-lines function, which exists right here. And it looks a lot different. You actually see what looks like small little lines, like worms almost, on our image. And we can actually play with parameters to actually get straight lines if you want. But actually, let's bring that up one more time. What's key to note here is that because of these new parameters where we have maximum line gaps actually eliminate the need, well, the problem where we have multiple lines drawn over each other on the same line here. If we set a maximum line gap at say 5 or 10, there's not going to be any lines running over the existing line that are similar. As well as we have a minimum length of 5 for our lines. 5 pixels is quite small, but generally we can start with that if you want to get mini lines here or lines in a character perhaps. And let's actually play with the threshold value and see what happens now. So let's set this at 50. There we go. I'm seeing slightly more lines here, but it looks generally similar. So let's actually set this at 10. Actually, it's less lines, sorry. So maybe we need to set this at a higher value. There we go. So that gives you a feel of these parameters here. Hopefully you would probably find whichever one more useful. Generally, I tend to use half-lines more, but there are definitely use cases for probabilistic half. And if you'd like to learn more about probabilistic half-lines, I've actually put a link at the bottom here. This is a link to the research paper where probabilistic half-lines were first proposed. So I hope you enjoyed this lesson on line detection. Thanks. Okay, so let's talk about blob detection. So blob detection sounds a bit weird. However, if you've been in the computer vision world for some time, you would have bound to have come across it by now. So what exactly is a blob? Well, a blob, just like a real-life blob, I guess, is just a group of connected pixels that share a similar property. So in this example of the sunflowers here, you can see the center of the sunflowers all have this similar green tinge here. That's basically what our blob detection has picked up. Now, the properties can be size, it can be shape, and we'll actually get to that shortly. So in general, how do we use OpenCV's simple blob detector? That's the method what we call in Python. So what we do first, we create or initialize the detector object. we input our image into the detector, we then obtain the key points, and then we draw those key points like we do here. So let's actually get into the code and do this. Okay, so let's open our simple blob detector file here. It's lecture 4.8. So here's our code for it here. It doesn't look too scary, it's pretty basic actually. So let's run this code, see what's happening here. So we've loaded our grayscale image of the sunflowers that you saw previously, and we've identified blobs in the center of the flowers here. Quite nice. So let's see how we do this. So firstly we read our image in, and previously we saw if by just putting a 0 here, we can actually call a grayscale image, load a grayscale image in here. However, this is 0 actually signifies you're writing in this line of function here. So you may have seen some OpenCV functions where we have numbers instead of the actual words here. That's just shorthand. So moving on. So the first part of this here is that we need to initialize our detector. So we call this function here, well this class actually, and we create the detector object. And using this detector object now, we actually run the detect method within this object here. We pass the input image into it here, and this gives us our key points. Key points being our blobs it detected. So there's no tuning of parameters here. Where there is some tuning of parameters now is basically here, where we draw the key points in the image now. However, these parameters don't affect the number of blobs that were identified. They just affect how the blobs look on the image itself. So this is pretty self-explanatory here. So input image, the key points we identified. So blank actually here is just one of those OpenCV type quirks. It's just a 1x1 matrix of zeros here, so pretty much ignore it and just use this going forward. This here is the color, which we use yellow. This is green and red here. And this is how we draw the points here. So I actually just changed this just now to rich key points, and we can see it's actually yellow now. However, initially we used the default one, which I believe was, let's undo that default there. Just looks a bit smaller, so there's no big difference there. Okay, so let's move on to our third mini project, where we actually filter different types of blobs. Because as you saw here, in simple blob detector, there's no parameter tuning here. Well, actually there is, and we'll get to it shortly. Alright, so you've reached the third mini project, counting circles and ellipses. So this is actually what our little mini project here is going to produce. We're going to count the number of ellipses and circles together here, and then count the circles separately here. And we do this by filtering blobs, which we mentioned previously. So let's get to it. Okay, let's open the code for this third mini project. That's lecture 4.9. And here we are. So let's actually run this code and see what's going on. So here we have our image here. We have some circles and some ovals or ellipses here. First, we count all the blobs or all the objects in the image. There we have 32. And now we count the circles separately, and we have 8. So let's see how we do that. Alright, let me first show you how we actually count the number of blobs and put it in the image. This one is quite simple, and you should be able to do this by now. So we firstly initialize our simple blob detector here. We pass our input image here to the detector. We get the key points, and we actually show the key points and bring it up on our image here. But what's going on here? Well, here's a very simple function. We just find the length of the key points that was generated by our detector here, and we just create a string here, and we pass the string to put text here. That's the text variable here, and that's all there is to it. That's pretty much how we count all the blobs that were detected here. But how did we distinguish between ellipses and circles? Like, how did we actually go into the key points and determine which was which? That's actually what we do over here. So here's something I haven't showed you before. We can actually pass parameters to our simple blob detector by calling this class here. This is simple blob detector underscore params. And as you can see here, there's a number of parameters here to filter on. So let me go back to the presentation and we'll discuss what these parameters are and how do we distinguish between them. Okay, so these are the parameters we're actually setting when we call simple blob detector underscore params. 4 main parameters we filter on here are area, circularity, convexity, and inertia. And we can turn each of it on or off by setting it in the code here. So just by setting params.filter by area equal true means we're actually going to filter by area. and we can set minimum areas or maximum areas and vice versa. So let's look at it here. So by setting an area is measured in pixels, to a minimum size and then giving it a maximum, if we don't set this maximum, it's not going to actually stop at any maximum. It's just going to give you the maximum of all blobs there. So setting the thresholds between here and setting is true means that we're only going to be seeing blobs that are between these two values here in area. Similarly for circularity. Circularity is a measure of being circular. It's probably the best way I can put it. 1 being a perfect circle, which means that the radius is consistent as you rotate around the circle, and 0 is being the opposite. So what about convexity? Convexity here measures basically the convexity of the object itself. So that's a pretty bad way to phrase it, but this diagram here illustrates it quite nicely. So look at the shape here, the convex shape. There's no real concave parts of the shape here. I mean, yes, there is, but it's not much. However, in this shape here, there's a definite concave thing going on right here. So if you were to draw a convex hull around this image, you'd realize that the ratio of this area here to this area here would actually be pretty similar. Whereas if you draw a convex hull around this image here, the ratio of this area to this area here is actually going to be quite high. So that's how we filter by convexity here. Now this value should actually be some value between 0 to 1, and that is basically what we consider the convexity values there that we set. So what about inertia? Now inertia is a weird concept to think about, however it's actually very well explained in this image here. So simply put, inertia is a measure of ellipticalness, which probably isn't a word, but it probably best describes what we're measuring here. Low being more elliptical, high being more circular. So it also falls back into this circularity setting here. So we can actually set the minimum inertia to be 0.01, with 0 being basically almost like a straight line and 1 being roughly a circle. So let's go back to the code and see how. So now, having understood those parameters, these are the settings we actually use when we're filtering on ellipses in our example file. So you can play around with these and play around with your own images as well. I encourage you to do that, because what works here for me will not always work for other images, which is why I tend to use very simple images here. This is just to illustrate a concept, not to do anything too fancy just yet. The fancy stuff is coming later on, so don't worry about it. And similarly, what happens now? Once we set the parameters here, we then create our simple blob detector after setting those parameters. So remember that. Set parameters first, then call simple blob detector here. And this actually pulls the params that were created right here. And then what we do, we actually just use the detector again to detect our key points. And having gotten those key points now, we actually do the same thing we did up here before, where we just find a length, create a string, and use putText to put it on the image. So again, that's quite simple here. And let's just run it one more time. Input image, all blobs counted, and now only our circular blobs counted. There we go. Welcome to section 5, where we talk about object detection. Now, object detection is what makes computer vision so powerful, and it's in this arena where there's so much cutting-edge research currently taking place. So in this section, we start off doing some simple object detection using template matching, which then leads us to our first mini project where we actually have to find Waldo. You can see it here quickly. Finding Waldo in this maze, or this mess of a picture here. We then describe the features. Now features are very important. Features consist of corners and other attributes associated with the image. And then we look at some common and popular feature algorithms such as SIFT, SIRF, FAST, BRIEF, and ORB. And there are a couple others like Freak and Brisk as well. And we then utilize these feature detection algorithms in our second mini project, where we do some actual object detection using these features. And then we describe a bit more on the histogram of gradients, which is one of the best descriptors used to describe objects and pictures. So let's get started. So why do we need to detect objects in images? Well, object detection and object recognition, they form perhaps probably the most important use case for computer vision, you can do so many powerful things like labeling scenes, such as labeling this as a digital billboard, a bus, people on a sidewalk, storefronts, or it also applies to robotic navigation in VSLAM algorithms, self-driving cars, which is actually a form of robotic navigation, body recognition through Microsoft Kinect, disease and cancer detection, things like looking at malaria slides or pictures of skin cancer, face recognition, handwriting recognition, even military use cases like detecting objects in satellite images, and the list goes on and on. There are literally so many use cases for object detection and recognition. So there is a key difference between object detection and recognition. Recognition is basically the second level of object detection. It allows the computer to actually recognize multiple objects within an image. Take example this picture of Hillary Clinton. An object recognition algorithm, probably a face recognition algorithm, would detect that firstly there's a human face in this picture, and then tries to match that face to a person in the database, this being Hillary Clinton. Now in this case here, this is one of our mini projects which we'll do in this section later on. We're just doing a simple object detection method here. So as soon as this object is held up in this little box here, it says object is found. This one only looks at one particular object and does not try to recognize exactly what it's seeing. It just waits for this image to be there, and then it tells you, yes, object has been found. So let's look at our first object detection algorithm that we're going to investigate. This one is called template matching, and it's actually a very basic algorithm. What it does, it slides a picture that it's looking for in a larger picture here. So the picture we're looking for is a picture of Waldo here. You can kind of see him slightly blurred. But let's bring him back down to this similar scale as this image. And what template matching does, it actually slides this picture across the image back and forth, waiting for a match. And as soon as the match is found, it actually tells you, yes, the match has been found in this point here. So let's get to it. So welcome to our fourth mini project, which is finding Waldo. Now, if you're familiar with those Waldo children's books, you basically have to find Waldo, who's this little character, in this messy maze of an image here. So we're going to now use template matching, which we just discussed, to actually find Waldo. So this is the input image we're giving it, and this is the output that we're going to get. So let's see how we do this in our code. Alright, so let's load up our code for my fourth mini project. That's here, lecture 5.2. And here we are. So let's see what's going on. Let's actually run this code quickly. It actually looks very short. So here's our input image of Waldo being on a beach. Well, we don't know where Waldo is yet, although I may have pointed it out before. Ah, there he is. So we found him. And that was really quick. So let's see what's actually going on here under the hood. So what's happening here is that we're using the match template function from OpenCV. Now this function is pretty cool and pretty easy to use. What's happening here is that we have our input image here. That's Waldo on a beach, the one that we couldn't find Waldo in. Then we have our smaller template image, which is the one we're looking for in the larger image. And this is our matching method here. And what this does is returns an array called result. And what result has in it is the result of the actual template matching procedure. And then we just use this other CV2 function, min-max location. What this does, this gives us basically the coordinates or the bounding box that Waldo was found in. And after we get that box, we basically just use those points to actually draw a rectangle over Waldo. What I've done here, you may wonder, like, I have some little odd things here, such as plus 50, plus 50. I'm just making the box slightly bigger than the image itself, so that we actually can highlight Waldo properly on the larger image. So there's one thing I just casually brushed over here, and that's the matching method being used. Now there are a few matching methods available in OpenCV. This one is called the correlation coefficient, and you can learn more about it here. I have a link at the bottom of this IPython notebook file. Just quickly visit the site here. This tells you the differences mathematically of what the different matching methods are doing exactly. So I've used all of these in this example and others before, and I don't see much difference between them, although some of them do seem to work better than others. So if you're using template matching for an application, just experiment with these different methods here and just choose one that works best. If you really want to learn about the theory, maybe actually explore what's going on in these mathematical formulas here, and you may actually have one that's more suited for your application right there. Let's take a step back from the code for a minute and think about what we just did. We basically cropped an image from this here, from the input image, and was able to match it back to the same spot in this image again. Now, that has severe limitations if you think about it. One, this image here has to be very similar to the image here, otherwise it's not going to get matched. And then what about scale? What about rotation? What about taking it at different angles or different perspectives? As you can see here, all those things I mentioned are problems with template matching. Rotation renders this method pretty much ineffective. Scaling as well. What about changes in brightness, contrast, and hue? What about distortions? So template matching isn't ideal in most cases. So how do we solve this problem? So one technique that helps us solve that problem is by looking at image features. And what image features are? They're basically summaries of pictures. We can formally define them as interesting areas of an image that are somewhat unique and specific to that image. Also, they're popularly called key point features or interest points. So you may have come across that in textbooks or other online classes. So in this picture of London Bridge here, we can clearly see that the sky here is all one color, and it's uninteresting. There's no way this sky here summarizes the image, except maybe in the amount of sky that's exposed. But then again, that's not that unique to most pictures. However, looking at little points along the bridge here, we can see that this feature detection or image features here is actually looking at key points that are interesting to the image and unique to it. All these lighting conditions, styles in the bridge, peaks here as well, they're what we deem interesting, and we can use this to summarize this image quite nicely. So maybe in future, if we have another image of the London Bridge, a lot of these points here will be common to both images, and that's exactly how we can detect and match these images together. So why is feature detection so important? Well, going back to object detection, they have a lot of these similar use cases here, and one key example we can look at is image alignment or panorama stitching. So looking at these two pictures here, we can see that these 2 points are similar in both pictures here, and by doing some perspective warping and stuff, we can actually match and overlay these images correctly together. Similarly, look at this image here. There are only 4 key points we can use here, and we can detect that the same object is in both images here. Well, I previously said that image features have to be interesting points, or it should be interesting points. But what defines interesting? Well, an interesting point is a point that carries a lot of information about that image, and typically there are areas of high intensity of change, corners or edges. And what happens, or what that means, is that these areas are distinct and unique to that image itself. However, we should be careful. Noise can also appear informative when it's not. So maybe before we actually use a feature detection algorithm on an image, maybe we should clean it up, reduce noise, add some blur. Just keep that in mind as we go along further. This is a summary of the characteristics of good and interesting features. They should be repeatable, meaning that they should be found in multiple pictures of the same scene. They should be distinctive and unique. They also should be compact and efficient. We don't want an image that has a ton of features. We want it to have at least a minimal amount of features that can describe that scene accurately. And locality. Again, that pertains to the last point. So, having just learned a little bit about features, let's start using some of OpenCV's feature extraction algorithms. So the first image features that we're going to take a brief look at is using corners as features. Now, corners aren't the best to summarize images in terms of image matching. However, they do have special use cases that make them quite handy to know. So how exactly do we identify corners in an image? So quickly, just imagine this is a window that you're looking at here, and this black box here is on a bigger image here, and we're moving this window across this black box. Because there's no change in intensity in this box, we know that there's no edge or corner found in this box, so this area is deemed as flat. But what if we move this box horizontally across this edge here? There is a change, but the change is only in one direction, so that's an edge, not a corner. However, let's come to the corner over here, and we're moving this in all directions here. No matter what direction we move it in, similarly like we moved it in all directions here, there are changes in intensity. Previously there were none over here, so this spot is deemed a corner. So the first image features that we're going to take a brief look at is using corners as features. Now, corners aren't the best to summarize images in terms of image matching. However, they do have special use cases that make them quite handy to know. So how exactly do we identify corners in an image? So quickly, just imagine this is a window that you're looking at here, and this black box here is on a bigger image here, and we're moving this window across this black box. Because there's no change in intensity in this box, we know that there's no edge or corner found in this box. So this area is deemed as flat. But what if we move this box horizontally across this edge here? There is a change, but the change is only in one direction. So that's an edge, not a corner. However, let's come to the corner over here. And we're moving this in all directions here. No matter what direction we move it in, similarly like we moved it in all directions here, there are changes in intensity. Previously there were none over here. So this spot is deemed a corner. So let's actually take a look at the OpenCV code that we can use to find corners. So let's bring up our IPython notebook manager here. Lecture 5.4, Finding Corners. And here we are. We're going to explore using two different methods of corner detection. The first we're going to use is called Harris corners, and that comes out of some work done by Stephen Harris in 1998. The paper is here, there's a link right here to it, that actually defines the algorithm used in corner Harris, or Harris corners, which is what it's typically called. So let's take a look at this code and see what's going on here. So first we load this image, and this image is of a chessboard, which you'll see shortly. Then we grayscale this image, convert it to float 32, because this is what corner Harris actually requires as the input for a function. So this is another OpenCV quirk that's not straightforward. However, just keep this in mind when you're using this function. And now we actually use the Harris corner function right here. So we input the image here, which is gray. And then we put some tweaking parameters here. These you can see here, these are block size and aperture size for the Sobel derivative that's used. I don't expect you to know exactly what these are because they're defined properly here in the paper. So if you want, you can just play around and toy with these values, see if it gets the results that you actually want. And then there's a free parameter here, which again, I don't recommend you play with too much unless it improves your results significantly. So once we run this corner Harris function, it returns an array of corner locations. However, to actually visualize these corners, because they're given us tiny locations, we can actually do a couple things to do it here. So one technique we can use is by using dilation to actually add pixels to the edges of those corners. So we run the corners here in dilations here, run it twice, and then we actually do some thresholding here, just to change the color of the corners that we are drawing on our image here. And let's run this function, and here we are. So these are the corners, Harris corners defined, and these are the corners that we dilated here. You can actually see that they're not aligned totally. It's actually, on my screen, it looks like a tiny optical illusion. I don't know how it looks on yours. And those are the Harris corners we detected on our chessboard. So let's take a look at our second corner detection method called good features to track. Now, good features to track is actually an improvement on the work done by Stephen Harris in 1998. And here's the algorithm, or the OpenCV function here. So let's run this code. And here we go, we've got some corners. Now there are some key differences in this algorithm, and I'll discuss this quickly. So again, we have a grayscale image here that we use as our input file. Then there's a value called 50 here. And what 50 is, these are the max corners you want to return in our image. We could set this to 10, and look what happens. We get the 10 strongest corners, and we could set it to 100, and we basically just get all the corners it could have possibly found. So it's finding some corners, some possible corners on the edges here. Then we've got some parameters here that just tweaks the corner detection, like sensitivity. So quality level here, this is a parameter characterizing the minimal accepted quality of the image corners. It actually is a bit complicated to explain. However, the max value we can set it as at 1500 and the lowest value at 0.01. Now min distance is similar to another algorithm that we looked at. I think that was in probabilistic Hoflines. This is the minimum distance between corners that we're returning here. So if we set this to 150, it's actually going to return a lot less corners. As you can see, the corners are more spaced out. So using good features to track, you can actually tweak your corner detection methods quite good. And similarly, just like Harris corners did, it returns an array of XY corner locations. So what we do here is a bit different to what we did previously, but this is actually easier to understand. All we do is we iterate through each corner in the corners array, get the XY locations, and then plot a rectangle. But what I'm doing here is I'm actually adding some dimensions. I'm decreasing, I'm pulling back sort of speak, the rectangular boundary here and adding 10 here. So that gives us a slightly larger rectangle to visualize our corners in our image here. Otherwise it would have been a bit too small, but that's just purely for aesthetic reasons. So as I mentioned initially in the introduction slide to corners as features, there are some problems with using corners. One, corner is not tolerant to intensity issues here. As you can see, we detected corners at these points here in this image. However, when we brighten the image, they're all gone, they're no longer visible. So also corners are intolerant to scaling as well. Look at this image here. This image, it's normal sized here. However, when it's reduced in scale or resized to a smaller image, possibly the corner detection algorithm will only detect one corner. So that's not very good. And here's an illustration of what happens when we enlarge an image here. So this was a corner that this little bounding box here found. But what about when this bounding box is moving over an enlarged image here? It's no longer going to detect a corner, it's actually going to detect edges. If we resize, the box would have to resize automatically in this case to compensate. However, that's not being done. So how do we get around some of these issues here? Well, that brings us to the other set of image feature detection algorithms that we're now about to discuss. So now let's introduce SIF, the solution to all those problems we encountered in everything else in life. Okay, just kidding about that last bit. So SIF stands for Scale Invariant Feature Transform and was developed in 2004. However, you should know that SIF is actually patented and no longer freely available with OpenCV 3.0 plus. So what that means is that if you need to use it if you have OpenCV 3.0 and you need to use it, you'll need to build it in to your directory separately. It's a bit tedious and I may put up a tutorial on it later on in the course. However, if you need to use SIF and SUF right now, which is free to use for academic and research purposes, but not commercial, you should install OpenCV 2.143, which is the latest stable version, which has SIF and SUF package freely in it. So what is Scale Invariant Feature Transform exactly? I'll get into the theory, but however, I just wanted to illustrate the SIF features in this image here. So these little circles here, these colorful circles, which were the informative descriptors that we chose to illustrate it with here, these showed all the key points that our SIF transform our SIF feature detection algorithm actually picked up. It's pretty cool. So as I'll move into the next slide where we discuss SIF, this is basically SIF in a nutshell because SIF is actually quite complicated. So I'm going to try something ambitious, which is to explain SIF in less than 2 minutes. So let's go. So firstly, SIF is able to detect interesting key points in an image by using a method called difference of Gaussians, and I'll illustrate that in the next slide shortly. But what this means here is that these are areas in the image where the variation in that section exceeds a certain threshold, and these are usually or typically better than edge descriptors. So once we identify those areas, we then create a vector descriptor for those areas. Now a vector descriptor is basically an array that possibly stores values that describe what it's seeing in that region of interest or key point. So what SIF then does is that it actually changes the scale of that region to enlarge it and then to decrease the size. Basically the pyramiding technique we showed you before. And what it does, it just tries to find a specific stability criteria. And once that criteria has been met, we then store the values for the most stable scale in our descriptor vector. This allows us to be scale invariant. So how do we achieve orientation invariance? Well, orientation invariance is achieved by firstly finding the orientation assignment of the key point, and we do this by using the image gradient magnitudes. So once we know the 2D direction, we can then normalize to this direction. If you would like to know more about SIF, I fully invite you to read the full paper here. There's also an excellent tutorial on SIF on the OpenCV documentation site at this link here. So here are just some quick illustrations I pulled from the paper itself. This shows you the difference of Gaussians method that's used here to find the key points. You can see it's being done in different scales here, different octaves. And this is how we normalize for rotation. These are the image gradient directions here. So moving on to SIF. SIF is basically the speeded up version of SIF. Because SIF is actually quite computationally expensive. I've actually implemented SIF in a robotics project, and it literally took maybe up to 10 seconds sometimes to calculate key points, and that's using an Intel Atom processor. So definitely SIF isn't always suitable in some applications. However, surf was actually developed primarily for speed here. So it achieves the speed boost by using, instead of the difference of Gaussian approach, surf uses a Hessian matrix approximation. It uses this to detect interesting points and uses the sum of a Haar wavelet responses for orientation assignment. That's a bit of a mouthful, but if you need to know more, there's actually a link I have in the code you'll see in the IPython notebook, so you can read the paper on surf as well. So, like I said, SIFT and surf are actually patented and can't be used in commercial applications. So if you're interested in using this for a startup project where your goal is to make money, there are some other alternatives to SIFT and surf. There's one called FAST, which is short for Feature from Accelerated Segment Test. However, this is just a key point detection and it's not a descriptor. So we can actually end up using SIFT or surf to actually compute descriptors based on FAST key points. And FAST is actually used, and it's appropriately named because it's used in real-time applications. Another interesting feature detection method is BRIEF. BRIEF stands for Binary Robust Independent Elementary Features, and it actually computes descriptors even faster than SIFT or surf. So again, staying true to its name, it's BRIEF. And lastly, there's one actually that came out of OpenCV's labs, so that's actually pretty cool. So it's not patented and free to use, and that's called ORB. And ORB is basically the combination of oriented fast and rotated brief. So it combines the best points of them. So feel free to actually investigate this further and check out the paper on ORB here. So before we go and use these algorithms in OpenCV code, let's just illustrate the little flow process of what's going on here. So firstly, when using these detectors, we have to create or initialize the detector. Then similarly, we feed the input image into the detector. We obtain key points, and then we draw those key points on the image. So it's actually quite simple. Alright, so let's load up our code. It's lecture 5.5, SIFT, surf, fast, brief, and ORB. And here we go. So I just have a note here that's saying that SIFT and surf is patented as well. So just remember that. So now, as we saw in our previous slide, this is the order of what we're doing in the code. So we're first creating our SIFT object here by initializing the SIFT detector. We're then running the detect function or method. It takes the gray version of our image here, and it outputs key points. So we can actually then print the number of key points. And if you're using Python 3, I'm using Python 2, so just keep the brackets here so we don't get any errors. And then we draw those key points here. So the flags we're using here for the key point part of it is to draw rich key point entries. Those are the fancy ones that you'll see shortly. And we draw the key points over our image with our key points being XY coordinates here. So let's run this code. And here we are with our informative key points or descriptive key points. So it's quite nice, quite colorful, and as you can see, the key points do highlight what we deem interesting parts of an image. However, like I said, sometimes noise or unimportant parts of an image are identified as well. But that's just the nature of it. Maybe one day we can actually tune these things properly. So now let's take a look at surf. Surf is done similarly to SIFT. You do initialize the detector, you do get compute key points and stuff. However, what's new here is that there's a Hessian threshold here, which basically tells us that any value that's larger than this threshold will be retained by our detector. So now let's run the code here, and here we are. So we've got a lot less key points here, and it's exactly what I said before. So let's, meaning that we can tune the key points we want. So let's actually set this at 500. Wow, it's a lot more key points. So that's interesting though. So surf actually works pretty well, pretty fast, pretty descriptive as well. So how about fast? You remember what fast stood for, right? Fast was, let's go back to it here, features from accelerated segment tests. And also note this was just key point detection only, didn't actually create vector descriptors for those key points. But anyway, similarly it's done the same way, where we open our object here, initialize it, use the detect method, and let's run this here. Wow, this is a lot of key point entries. And the number of key points produced is actually 8,963, so it's quite a bit. So now let's take a look at brief. So we implement brief in a similar fashion as we have done previously. However, I just wanted to show you something here. By inputting key points into the compute method from brief, we actually can generate the descriptors here. Remember, descriptors are what we got from surf and sift as well. So let's take a look at brief here. Again, these are a lot of key point entries. 8,738, just slightly less than fast. So how about orb? Let's take a look at orb. Orb comes from OpenCV's labs itself, so it should be pretty cool. One thing that's different about orb, even though it's implemented similarly, is that we can actually set the max number of key points that we want here. So I have 1,000 by default here. So let's run this code. And here we are. So let's set this to even larger number, 5,000, see how it looks. And a lot more as well, as we expected. Or just keep in mind, if you're using Python 3, although I'm not 100% sure if this is the case because I don't have Python 3 installed right now, always remember to put your brackets by the print statement. One thing to note is that even though we put 5,000 as the number of key points we wanted here, it only returned 4,995, which means that 5,000 exceeded the amount of key points that orb could find. So what if we left out this argument totally? What does orb default to? And the answer is 500. So by default, orb tries to find 500 best key points in our image. So now that we have found key points and descriptors of images, what do we do with them? This all seems like a nice fun exercise, but is it really useful? Well, that's what we're going to see in our first mini project in this section, which is object detection. Hi, and welcome to our fifth mini project on object detection. We're going to be using both sift and orb in this project, and in this project we're going to be able to detect this object here. So when we hold this object here using our webcam, it's going to say object form. But if we put any other object here, nothing's going to happen. Okay, so let's see how we do this. Okay, so let's take a look at our code for our object detection. So this is the code here for a sift-based matcher, and then this is the code here for orb-based matcher. So let's actually run our sift-based matcher first and see it in action. Okay, so here we are. This box here, this blue box, is the region of interest we're interested in. If the object comes inside of the box, it says object found. However, if the object is outside of the box, it's no longer there. So this is pretty cool. Object found, object has disappeared. Alright, so let's put this down and close this. Alright, so let me explain what's actually going on here in this code. So we have one function that we've called our sift detector that's right here. This is doing basically the bulk of our processing here. This is actually what's doing the matching. So let's take a look at the bottom half of the code and see what's going on. So firstly, we open our webcam stream, which we've done previously. We load our image template, and the image template was the screenshot on my phone that I was holding up. That's the image that the program is actually looking for. So that's box and scene. It's actually what is used on OpenCV's official documentation tutorial site. So I'm just paying some homage to them here by reusing the image. So let's see what's going on in this loop here. So we're capturing images from our webcam, capturing the height and width, and then what are we doing here? Well, remember the blue box, the region of interest I told you that the image, the object has to be in? This is just defining those dimensions for that box. So I'm just taking 1/3 of the height, maybe 1/4 of the height here, the width. Basically just drawing a synthesized box that our object can fit in easily. You can play with these parameters if you want to expand the box or remove them totally and don't even have a box. So this is a rectangle we draw using those dimensions we defined, and what we're doing here is cropping that rectangle out, and that's actually what we're feeding into a sift detector. That's defined right here. So now let's take a look at the sift detector part of the code. Oh, before I go on, I just flipped the frame that you're seeing on the webcam. This way it's more like a mirror image, so it's more natural. So when I move left, my screenshot doesn't move right, which I actually find confuses me, especially when I'm holding up an object. I'm like messing around, moving this object around. So you can thank me later for that, for making it easier for you. So let's take a look at our sift detector here. So this is the function we defined previously. So this function takes our cropped image here, that's the region of interest that we're looking for the object, and the image template, that's the box and scene picture that was on the cell phone. And then it gives us some matches here. And what are these matches exactly? Well, we'll talk about that shortly when we go up to the SIFT code here. And basically what we say here, we put the number of matches found. Matches are basically how many matches or how many key points have been detected that are similar in our object and in the target image. So let's move on. So once we set our threshold here at 10, which means that once we have more than 10 matches in our image, in our object that's being scanned, we basically say that object has been found. So that's what this little if statement does here. If matches exceeds our threshold, we just display on our screen at a point that was appropriate. We just put object has been found, and then after all that, we just display with the final image, which contains all of these information that we previously highlighted. Okay, so let's take a look at our SIFT detector code here. So let's take a look at our very important function here, SIFT detector. So as I said previously, this function takes in two images here. It takes in the cropped image here. This is where it's looking for the object, and our image template. This is the object that it's trying to match to, which is the box and scene picture that we defined here, image template. So let's see what's going on here. Firstly, we grayscale our images, and we make image 2 here in our code here equal to the image template. That's just notation, so we don't get too confused going forward. So then we define our SIFT detector as we did previously in this other code. And what we do, we run our SIFT detector. Previously we just ran detect to detect key points. Now we're doing detect and compute, which is to compute our descriptors. Now if you remember previously in our slides, descriptors are basically vectors that store information about the key points. And it's very important because that's how we actually do the matching. We match between descriptors here. So we do this detect and compute using SIFT for both images. And then we come across something here that we've never seen before. That's our flan-based matcher. So let's discuss that a bit. Alright, so let's talk a bit about our flan-based matcher. So I'm not going to get into the mathematical theory of matching. However, I'm just going to show you quickly how to use this. So we just define our parameters here for our flan-based matcher. So we just set our index KD3 here at 0, so initialization value. And then we set some index params and search params. So these parameters are set in a dictionary format. We just define the algorithm that we're going to use, which is KD3. How many trees we're going to use. The more trees, the more complicated it gets, and possibly slower in most cases. And how many checks. So this is basically how many matches is it going to try to compute. So we're going to go up to 100 matches here. So then we create our flan-based matcher object, calling it flan, loading these parameters we defined previously, index and search. So moving down now, this is what we're actually using here to compute the matches between the descriptors 1 and descriptors 2, which was for image 1 and image 2, using our flan, using KNN matching. Now KNN stands for K nearest neighbor. Basically, it's a way that where we sort of look for the nearest matches on descriptors. So imagine you have a bunch of descriptors for descriptors 1 and descriptors 2 on a graph. And we want to see exactly how close these matches are to each other, sort of like a distance measure. So we have our KNN matching done here. We have K equal 2. That's just another initialization constant. This basically just keeps it the same way every time we run the code. It's not too important. So you can try different values. It probably wouldn't change much. And what we have here, what this returns, it returns the number of matches found in the code. And I've noticed I left some comments out here. So the result matches is essentially the number of correct matches found in both images. Or I should say not correct, but similar matches. But you get the idea what it's doing, I hope. So the next part of the code here, it just may confuse you slightly, so I'll just talk about it quickly and tell you why we're doing it. Firstly, flan-based matching is an approximation of matching. It's not highly accurate, but it is very fast. However, to improve the accuracy of flan-based matching, what we do is we use something called Lowe's ratio tests. And what Lowe's ratio test does, it looks at the matches generated from the KNN match here, flan KNN match, and it just defines some metric parameters here. So if m.distance, and distance is a numpy function here, this is why we needed numpy before, and once it meets this criteria, we just append our matches here, m, to the good matches metric here. And this function simply just returns the number of good matches found. It doesn't actually return the matches because we don't need them anymore. We've already processed them here. So all we need to know if an object has been found is how many matches exist between the image in our, let's look at it here again. How many matches have been found? Let's bring up my image on my phone. Between this image that we're looking at and the image that with the template image. So let's see how accurate this is. Let's just try something else here. This is a bottle of omega-3 fish oils, which I should take. I don't actually take them that often. Here's a pack of maca. No matches at all. So this is actually quite accurate. Let's just try a menu for a restaurant. See, no matches at all. Well, we got 6 there, but 6 is probably just some generic matches, which is why we defined our matches as more than 10. So this is pretty cool and pretty accurate. And let's just take a look at some of the other things here. So I have the number of matches found below. We have up to 50, sometimes 60. Let's bring this up closer. We got up to 60. Wow, 70 there. Okay, so that's pretty cool. So setting our threshold at 10 is probably being too lenient. Maybe we should be a little more strict and set it to like 30 or something. So you've seen SIFT matching here. We're now going to move on to orb matching, which follows a very similar procedure. However, instead of using SIFT here, we use orb, and we also use a different matching algorithm here. So let's get to it. Okay, so let's take a look at our orb-based matcher now. So as you know, SIFT is pretty cool and it's very accurate. However, it's patented, and we can't use this for a commercial application. So I'm not even sure if I'm supposed to be making money and teaching you using SIFT. Maybe I should just keep quiet about that. So anyway, let's look at orb. Well, actually, before I get to orb, remember I told you we're going to use a different matching algorithm? Well, aside from flan-based matching, there are some other matches that exist here. I'm not sure if all are available in Python's OpenCV. However, when using orb, you do need to use BF matcher, which is actually a much more accurate matching algorithm here. So let's run our code here. So just quickly, I just want to tell you, nothing really is changed here. The only thing that we have changed in this section of the code is our threshold and the name of our function, orb detector. Okay, so let's quickly run this code and see how well our orb object detection algorithm or method actually works. So let's go ahead and run it. And there we go. So already we see there are some noisy matches being generated. Previously on SIFT, you would see maybe 5 to 6 max, just random noisy matches. Basically my face being, apparently it's similar to the object, somewhat. But let's see what's going on here, because remember in orb we were going up to 1000 key points. Alright, excellent. So we see performance is pretty good as well. It detects the object, maxing out at maybe around 420, perhaps a little more. So that's pretty cool. Alright, so let's take a look at our code and see what's actually going on in our orb detection function. Okay, so let's scroll up to our orb detector, and we'll immediately see that it's actually shorter than our SIFT detector. Maybe it's simpler, but let's see what's going on. So firstly, it takes 2 images into consideration, the same as we have seen previously, our image template and the cropped region of interest we're looking at in our webcam image. We grayscale the webcam image, and then we define we initialize our orb detector, and we just set it at 1000 key points and a scaling pyramid factor of 1.2. So you can play around with these values. However, be careful. Sometimes it breaks, or it doesn't really break, but however it is sort of tuned for our application here. So just you can experiment with your own applications as you desire. So we then detect key points, and it's just shorthand for key points, and descriptors here for both images. And we define a second parameter in the detect and compute function called none. None basically defines whether you want to use an image mask or not, so we're not using an image mask in this case. And then we move down to our detector. And this is different. We're using CV2 BF matcher. Previously we used flan. And we define this parameter here, norm Hamming, which is a distance metric, and cross-check equal true. So this is defining our BF matcher, and then we actually compute the matches between those two images using our descriptors here. So we get a number of matches from this algorithm here, and we no longer need to actually use Lowe's ratio tests. However, what we do, we just define a function here. We use this function called distance, and we just sort our matches on distance here. So the least being the better. However, please note, this is just an exercise here. I just left this code in here, mainly to show you that we can sort a number of matches. So you can discard the smaller matches, and lower matches are better. So we can discard the larger distances. Least distance is better, remember that. That means distance between the points. So again, we just return the number of matches found, and that's how we actually define it here. So as soon as we cross 350 matches, basically we say the object has been found. Now there's something I want to show you, and maybe I'm not tuning this too well. Perhaps you can do better than me. But running the code again, you can see orb does sometimes say object found for images. Look how many matches are being generated. It's 300 sometimes. So you see object has been found. So that's it's not as good performance at all as SIFT. So unfortunately, if you do want to use SIFT for your application, and it's like a startup idea or money generating application or commercial application, you may have better performance with SIFT. So you may have to use that and pay the patent fees. Thanks. So let's talk about a different descriptor, and that's histogram of oriented gradients, short for HOGs. Well, HOGs are short for histogram of oriented gradients. So HOGs are actually a very cool and very useful image descriptor. So you saw previously using SIFT and ORB, we had to compute key points, then compute descriptors out of those key points. Well, HOGs do it a bit differently. HOGs actually represented as a single vector as opposed to a set of feature vectors where each represents a segment of the image. Hopefully that's a bit clear to you, but what this means exactly is that we have a single feature vector for the entire image that's computed. And this is how it's computed. It's computed by sliding a window detector over the image, and we generate a HOG descriptor which is computed for each position in the image, and that each position is then combined into a single feature vector later on. And again, we do use pyramiding as a technique for generating this feature vector, I should say. So how do we use HOGs? Because previously we had matches like FLAN and BF matcher. Well, HOGs are actually traditionally best used with SVM, which stands for Support Vector Machines, which is a machine learning classifier, and a very good one at that. So traditionally, again, how we do it is that each HOG descriptor for that image is computed and then fed into the classifier to determine whether the object was found and where it was found in that image. So let's get to a brief explanation of HOGs. So understanding HOGs can be a bit complicated for a beginner, so I'm going to try to break it down as simple as I can without going into the hardcore mathematics of it. So here's a picture I used of my wife, and I've sort of pixelated it a bit so we can sort of see that this is an 8x8 pixel box here. It's actually not 8x8, it's probably a lot more in reality. However, just defining the box size here. So what we do in this box, we compute the gradient vector or edge orientations. So what that means here is that in this pixel box, remember what image gradients were? Sort of the directions of the flow of the image intensity itself. Well, that's what we compute inside this box. And this generates 64, well, we generate 64 gradient vectors, which are represented then in a histogram. So imagine a histogram that distributes each gradient vector. So if all the points or intensities lie in one direction, the histogram for that direction, let's say that was, say, 45 degrees, so I think if this was 0, then it would have a peak at 45 degrees here. So what we then do is, as I just mentioned, we split these angles of orientations into angular bins. And in the Dalal and Triggs paper, who initially proposed histogram of oriented gradients, they used 9 bins, 20 degrees each from 0 to 180. So what we have done there, we've effectively reduced those 64 gradient vectors into just 9 values. So we've reduced the size and yet kept basically all the information that we needed, all the key information. And just a key note here, as it stores gradient magnitudes, it's relatively immune to image deformations. So moving on to the next slide. So the next step in computing HOGs is actually called normalization. And we do normalization just to make it invariant to illumination changes such as brightness and contrast. So how we do that, I'm going to quickly describe the mathematics here to show you how we actually define the normalization factor. So in this original image here, you can see here's the colors between, so this is 101, top half of it here, 61, 91, and 51. So it's a distance of 50 in all horizontal and vertical directions. So we get our normalization constant here at 70. Similarly, if the image increased in brightness, we can actually compute and see it the same, 70.72. However, if a contrast increased, contrast means that the bright areas got brighter and dark areas got darker, sort of. We actually see distance has increased. However, we can still compute the normalization factor here. So by doing that, we divide the vectors by the gradient magnitudes, which we get, well, this is this divided by 100, 7.07, and that's our normalization constant. Similarly for here, when we do it with the contrast one. So normalization doesn't take place on a cell level. It actually takes place on a block level itself. So blocks are basically groups of 4 cells here. So what we do, we just take into consideration our neighboring blocks, or cells I should say, when computing our normalization constant. So the normalization factor is computed for each here and then averaged out and then divided by it here. So that's it for hogs. Let's take a look. Oh, that's the explanation for hogs. Let's take a look at computing hogs in our code. Okay, so let's load up our code. This lecture 5.7 for histogram of oriented gradients. Alright, so firstly you can see the code looks a bit complicated, and I'm actually not going into the details of this code. This exercise is just going to be just a very high level explanation. If you do want to learn more about it, there's some links you can click here just to understand the hog descriptor a bit more. There's also a lot of cool things being done with hog descriptors and SVM, so I encourage you to look into that. You can just search Google and you'll find tons of resources. So what I'm going to do here is I'm going to load the image of our elephant that we used previously, I believe. Grayscale our image, just show our image here, and then we define the parameters. So remember, we're defining the cell size as 8 by 8 pixels. Our block size is 2 by 2. Remember, the block size was what we normalized to here. Number of bins, which was 9 previously, each one 20 degrees. And this is where we defined OpenCVs here, CV2 hog descriptor. This is what we use to define that hog descriptor right here. So this may be a tad confusing. It was to me at first. However, win size is just the size of the image cropped to multiple sizes here, and you'll see win size somewhere inside of here, right here, yep. And then later on, we compute the NumPy shape array for our hog features, and that's called n cells. Then we get our n features from hog.compute. Then we get our gradients. So then we compute our gradient orientations here. Well, this is just setting up our array for it here. And then we actually create the array for the cell dimensions here, cell count. Then we implement our block normalization. I'm sorry if I'm going over this pretty quickly. It just will take very long to actually go through each line properly for you guys. And then we average our gradients here using our cell count. And then we just plot our hog, or histogram of gradients, using matplotlib, which is why we imported it initially here. So just take note of that. So let's run this code and create a visual for our hogs. So let's run it here. This is our elephant, our input image, and these are the hogs for that image. So these are, let me explain quickly what this is. So you can see it's a bit granular here, and you can sort of make out the shape of an elephant here. But what's happening here is that each of these blocks here are 8 by 8 pixels here. And basically these are the gradient directions that we give here. So you can see this is actually how we actually store hogs or hog descriptors for images here. So all of these values here basically are essentially form our descriptor, our hog descriptor of this image. Okay, so that's it for hogs. How you use hogs essentially is once you have those hog descriptors that we just created and we just visualize right there, you can then feed that information into SVM classifier and compute, well, or do some object recognition or object detection using it. Okay. Hi, and welcome to section 6, where you're going to learn to implement face, people, and car detection. So let's take a look at this section in more detail. So firstly, before we implement these detectors, we're going to learn how we build these classifiers themselves. So you're going to understand Haar cascade classifiers. Then we're going to use those classifiers in doing face and eye detection. And then that brings us to our sixth mini project where we detect cars and pedestrians in video frames. So let's begin with understanding what Haar cascade classifiers are, and then we'll get into how they work. So in the previous section, we saw that we can extract features from images and then use those features to classify or detect objects. So Haar cascade classifiers are essentially the same thing, except they have a different way of storing those features, and those features are called Haar features, which we'll get into in a moment. So what we do now, we feed those Haar features into a series of classifiers, which is called a cascade of classifiers. And then we use that to basically detect whether that image is present in the image or not, or that object, sorry, is present in the image or not. So Haar cascade classifiers are very good at detecting one particular object, example a face. However, we can use them in parallel to detect faces and eyes, maybe mouths, etc. So I'm going to try to explain the theory behind Haar cascade classifiers. It can be a bit tricky, however, it's actually very good to know. So let's start. So firstly, we train the classifier by giving it a bunch of images, and when I say a bunch, I mean like sometimes thousands or hundreds at least. So we give it some positive images, and those actually can be less than the negative images. So let's say we give it 500 positive images, and those could be images with a face if we're building a face classifier, and then we give it maybe thousands of images with no faces present. So that's the first part of basically training a Haar cascade classifier, is gathering those images. So once we have those images, we now have to extract our Haar features out of it. So I'll explain to you what Haar features are. They're basically the sum of pixel intensities under rectangular windows here. So these are examples of different windows that are used. So in the first proposal for Haar cascade classifiers, I believe, that was in the Viola-Jones paper, or it could have been something before, they used these different rectangular features here. And what we did, we recorded the sum of feature intensities under each rectangle here. However, doing so for an entire image, even if the image is resized and we use a large window, it results in literally thousands and thousands. So in the first paper here, I think it was 180,000 features were generated. And that's a very slow process to actually calculate the sum intensities under all these different windows. So what the researchers did, they developed a method called integral images that actually computed these sum intensities using Fourier references, and it was much, much faster. These are some other rectangular features that could be used as well, just in case you want to create your own Haar cascade classifier in future. So even though the researchers found a way to calculate the sum intensities much faster using integral images, they still ended up with quite a large number of features, 180k to be exact. And the majority of them added no value because they were landing on areas that didn't have a face. So what they did was they used a technique called boosting, and then used an algorithm called AdaBoost, which actually found the most informative features in the image. So AdaBoost is actually a really cool algorithm. What it does, it actually uses weak classifiers to build strong classifiers. And it does that by assigning heavier weighted penalties on incorrect classifications. So what they ended up doing was reducing these 180,000 features to 6,000, which is a huge reduction. So now if you think about it intuitively, even if we have 6,000 features, that's still a lot to process at once. And obviously in those 6,000 features, some are definitely going to be more informative than others. So what the researchers did, they developed a system called a cascade of classifiers, and that's where the name originates from, obviously. So what this does, it actually looks at the most important feature first. And what it does as well, it's sort of geared or tuned toward classifying faces easily. So let's assume in this first region here, it may classify this as a face, so that's a false positive. However, typically what happens is that as it moves to stage 2 and it checks 10 more features, this area may be eliminated as a face. So as you can see, by sliding this window across, we're actually just calculating based on 1 or 10 or even 20 features sometimes, until it reaches a face region. And then it's actually going to go through all 6 stages before it actually says it's a face. That's why Haar cascade classifiers are actually so good and so fast at detecting faces and rejecting everything else that isn't a face. So this was basically the system of the Viola-Jones face detection method. You should actually give their paper a read. I'll put the link in the IPython notebook file. So we're now about to implement actually this face detection algorithm and eye detection algorithm in our code. Hi, and welcome to our lesson on face and eye detection. So we're finally going to use some cascade classifiers to detect both faces and eyes in pictures and even in video streams. So we're going to use some pre-trained classifiers that have been provided by OpenCV, and you can access them through this link here, although I have given them to you on the course files. They're supposed to be in your HAR Cascade folder. So anyway, we can take a look at OpenCV's site to see the classifiers they provide. It's actually quite a few of them, and today we're going to use HAR Cascade Eye and full frontal face default, I believe, which is here. Yeah. So you may have just noticed, actually, let's go back quickly, that these classifiers are XML files. And XML stands for basically Extensible Markup Language. It's basically a language we use to store vast amounts of data. You can even store a database in an XML file. However, it's designed to be human readable, so there's not too much you need to know about this format when using HAR Cascade classifiers. You just need to know that it's stored as an XML file. And I'll give you a simple overview of the flow of how we actually use these cascade classifiers in OpenCV. So simply like using SIFT and some of those other algorithms before, we load or initialize our classifier, and then we pass our image or the video frame to the detector classifier method, and that method typically returns an ROI or region of interest, which is the location of the face here, or eyes perhaps. And then simply once we have that region, we can actually draw a rectangle over the face like we have done in this sample image here. Or you can actually use the face, you can crop it and maybe apply some sort of face mask or filter. So that's pretty cool. So let's actually look at implementing face and eye detection using OpenCV. Alright, let's go ahead and open our code. Select just 6.2 face and eye detection. Bring it up here. Okay, and we have a few blocks of code. So let's look at the first block here. This one is just doing face detection. So let's quickly run this. And there we go, it successfully ran. We have a pink square or rectangle around Donald Trump's face. That's pretty cool. So let's see exactly what's happening here. So let's look at the first line of this code here. So we're using CV2 cascade classifier, this function, which we point to our HAR cascade classifier that we're using here for face detection. That's HAR cascade frontal face default. And that would have been one of the classifiers I gave you in the files for this course. It's in the HAR Cascades folder, and there are 3 other classifiers here as well. So what this does, this creates our face classifier object here. And then what we do now is we load our image. So this is the image of Donald Trump that you just saw actually. And then we find the grayscale of that image, which is pretty much standard right now. You may have noticed a lot of OpenCV functions require the images to be in grayscale. And then we use this method that's in the face classifier object, detect multiscale, and you're seeing the 3 parameters here, input image, and I'll get to these 2 parameters right after. And what this does, this actually gives us the region of interest that for each face it detects. So this faces file is actually an array. It's not the location of one face, but it's the location of many faces. So similarly, you saw previously how we had a list of lists. Think of it as that, as basically locations for different faces it would have located or detected in the file. So similarly, if the faces file is empty, that means no faces have been found. So we actually print that here. So if you're using Python 3.0, or Python 3.4 actually, let's keep it standard. Okay. So then we simply have to draw our faces over the image, and that's what this loop here is about. So as you can see, we have 4 values here in our faces array. So what we're doing, we're stepping through each of these 4 values in this array by using a for loop. And what we're doing, we're plotting, or drawing, I should say, a rectangle. And this is the color pink here, in case you're wondering. We're just plotting it here, using the rectangle function, and then just showing it here. So it's simple, so let's run this one more time. There we go. Let's now combine face and eye detection. So let's move on to the second block of code here. So what's different here is now we're loading 2 classifiers. We're firstly loading face classifier as we did before, but now we're also creating an eye classifier object here. So again, we load our image, default image here, and grayscale our image, and initialize our face classifier here. So similarly as well, if no faces have been found, we print no faces found, I actually just changed this quickly to be compatible with Python 3.4. So what happens when faces are found is that we're actually drawing rectangles again over the face, showing that image, waiting for a key to be pressed, and once that key is pressed, we crop that face. So remember how we cropped images using NumPy's array indexing? So we've cropped the face out of it. These are from the locations of the face that was stored in faces here. And we actually feed that image now to our eye classifier, but we actually feed the gray image in here. So we feed that to our eye classifier, and then we have eyes. Those are the eyes that was stored in the image. And you know, most humans should have 2 eyes. So we'll see if Donald Trump has 2 eyes just now. And we actually draw those eyes over here. So each time someone clicks wait key here, or clicks any key on the image, it plots each eye at a time. So let's go ahead and run this code. There we go. It waits for key. Let's see if it picks up the eyes. Yep, first eye has been found. Second eye has been found. Excellent. Alright, so we've actually made a face and eye detection successfully there. Let's now see if we can do it with a live video stream from our webcam. So let's scroll down to the third block of code here. And this is where we actually do the same face and eye detection. However, we're doing it now from a video stream from our webcam. And what I've done differently here, usually in most applications you actually find the rectangle of the face highlighted in the image. However, what I've done, I've actually cropped my face out of the image. So let's run the code and I'll give you an idea of what's going on. So there we go. There's my face cropped out of the image. And it's only my face. So you can run this code. I mean, it's just a novelty effect. It's no big deal. If you want it differently, like if you want to actually show the background with the face, you can actually try something different on your own by editing the same code here. So what's going on here is that again we're loading our classifiers. However, I've created a function that we feed the webcam image in, and this function basically takes the webcam image, finds faces using the similar code that we did before, crops out the face, then finds the eye again as we did previously right here. But instead of drawing a rectangle for the face, although it is being done here, we actually just crop that rectangle out, and once we've cropped that image of our face, we detect eyes in that image right here, and we draw the rectangle, the colored rectangle, over each of our eyes. We don't have any wait keys here because we wanted to do it at the same time. And then we simply flip that image here so it's, you know, in sync like a mirror image for ourselves, and we return that image. So let's run it one more time. There we go. It's pretty simple. So I invite you to actually keep playing and tuning these little things. You can make some cool little apps with these face and eye detections. So have fun. So what I'm actually now about to do though is actually show you what these parameters in detect multiscale here. So you may have noticed we use detect multiscale in our eye and face classifier right here, and there are 2 parameters here, 1.3 and 5, which is what we use typically for faces. But I'll explain why, and I'll explain the effects of increasing and decreasing these numbers. So let's scroll down to some notes I left here. So, as I said, detect multiscale has 3 input parameters: your input image, our scale factor, and minimum neighbors. So what does scale factor do? Firstly, scale factor, it specifies how much we want to reduce the image each time we scale. So what that means is that when you're pyramiding, how many times, like by what factor are we increasing or decreasing the pyramid image by? So setting it at 1.3 means we're increasing or decreasing the image by 30% each time it's scaled. So you know, if you're doing, if you make that value smaller, like closer to 1.05 or a value that's close to 1, but not exactly 1 because 1 is not going to do anything, you actually have a lot more computations to do because you're actually scaling in smaller and smaller increments. So now let's discuss the minimum neighbor setting. So quickly let's read this here. It specifies the number of neighbors each potential window, as remember those Haar cascade windows, should have in order to be considered positive detection. So typically we set it at 3 and 6. So what this means, if you think about it, is that let's run this first face classifier of Trump. So what's going to happen here is that usually when there's a window this size, the window that's right next to it, like if we draw an image right here, is also going to detect a face, and similarly again. So you may have multiple windows over the same face. So how do we know that's one face and not many faces? Well, we don't, but what we do is actually set this value here. So if we got, say, minimum of say 3 faces in that same region, then we know that's one face. That's what minimum neighbors indicates. So a low value will actually detect multiple faces over a single face, and high values actually reduce the sensitivity of our detection unit or algorithm. So typical ranges are between 3 and 6. If you want to reduce your false positive, I suggest you set this value maybe higher, maybe even 10 if you want. And if you want it to be very sensitive in picking up faces, set it at maybe 1 or even 2. So that brings us to the end of face and eye detection. Hope you learned a lot in this lesson, and you're now ready to implement a pretty cool, and it's actually very simple, mini project on pedestrian and car detection. Okay. Alright, so let's start our 6th mini project, which is on car and pedestrian detection. So let's take a look at the code and see how we implement this. Alright, so let's go ahead and open our 6th mini project. That's lecture 6.3. And here we go. So I actually want you to run a test. Just make sure OpenCV is installed properly on your machine, because there's a very common issue that prevents OpenCV from actually playing videos. So let's run the code, and this is how it's supposed to work. So that's actually our pedestrian detection going on right there. So let's close it off, and now if nothing happened, if this code ran and executed successfully, however it didn't load any video and didn't even throw an error, that means that your paths for this file, OpenCV4 DLL, hasn't been found. So what you'll need to do now, you'll need to actually find where this file is. It's stored in your OpenCV directory, so let's just get it here. So this is where OpenCV is installed in my machine. Just rename the directory here. So go to OpenCV, go to sources, go to third party, FFmpeg, and this is the file here that we're actually going to copy. So we actually copy that file to where your Python is installed. So this is where my Python is installed, in Anaconda 2 apparently. So to find the directory Python is installed in your machine, just run these 2 lines of code, and it tells you where the Python exe is stored. So what you need to do, you need to drag or copy this file to this Anaconda 2 directory. At least that's in my machine where it's installed. So let's quickly do that. So I'm in the base directory where my Python exe is installed, and you can see I have the files here. However, there's one important thing to note. You are going to have to rename the file. So I've just kept the original here, and you can just make a copy of it and rename that copy with the version of OpenCV that you're currently using. So I'm using 2.413. So that's a version I've called here in the name. So similarly, if you're using 3.1, you can just put 310, no decimal points either, and underscore 64 if you're using a 64-bit machine. If not, if you're using an x86 32-bit machine, which most of you shouldn't be, you just leave out the underscore 64. Okay, so that's it. So once you've done that successfully, and the instructions are here in case you didn't follow it properly in my video, you can just execute it and try this again, and hopefully it should work. So now let's go about explaining what this code is doing here. So this code is actually pretty simple, and it follows the similar method that we have actually just done for face and eye classification. So we're using a different classifier now. This is a full body classifier, and this is what we're using to basically classify pedestrians. So let's create our body classifier object, and what we're doing differently here though is that instead of actually having this argument as 0 as we did for video capture with our webcam, we're actually pointing it to an AVI file. That's the walking file. That's a file with the pedestrians walking. It's actually a standard file that's actually used in a lot of research, so it's why I'm using it here for you guys. So again, while a cap is opened, or you can have while true and have a break statement here. It's up to you. We're reading each frame of our video file here, and we're also resizing the frame to half its size. And the only reason we're doing that is actually to speed up our classification method, because larger images obviously have a lot more windows to slide over, a lot more pixels I should say, to slide over. So it's actually going to slow it down quite a bit. So we're decreasing the resolution of that video by half. That's what the 0.5 indicates here. And also using one of the quicker interpolation methods, interlinear. Okay, so then we also have to grayscale our image as we had done previously. And we feed that image into our detect multiscale, which is our classifier. and set our parameters here. And as you remember, this was a scaling parameter. Larger values makes the detection faster, I should say. And this value is basically a sensitivity factor. So by reducing it, it actually becomes more sensitive, but it also produces a lot of false positives. So these parameters work well, and you'll see shortly. And what it does, again, it returns bodies being an array of points, and then we can actually just plot those points here using our CV2 rectangle function. So this is how we actually draw the little boxes around our pedestrians that we've identified. And we just exit this loop here by pressing enter key. So let's run this and quickly look at it. So let's bring it up. And there we go. We see it's actually detecting most of the pedestrians here. Sometimes it misses it, sometimes it doesn't, but it's actually fairly accurate and fairly good. Okay, so let's move on to car detection now. So this code actually is pretty much very similar to the previous code. The only difference is here is that we're pointing it now to our car classifier here. And pretty much the same thing is going on here. So let's just run this code and let's take a look at what's going on. So again, we see it's actually pretty accurate. It's actually picking up a lot of the cars. It's not always very accurate, especially with cars in the distance here, and Mr. Truck, and also Mr. Bicyclist here. But it's pretty good. So I encourage you again to play with these parameters, see if there's any other better options you can have here. So the line here, maybe I was experimenting with some parameters. You can delete it for this purposes here. You also may have noticed I actually have this time comment .sleep commented out here. Now what this does actually, you may have noticed that the frame rate in these videos is a bit fast. So what time does, it's a way just to add some pauses in our code. So you need to import time, and let's actually execute it here. So this with 0.1 adds a delay of 0.1 before executing the rest of the code. So you can see, yeah, it's definitely much slower. You can actually use this for testing if you want to just make sure you're testing it correctly and getting all the cars you want to see. By making it smaller, just in case you're wondering, it actually speeds up the frame rate. Type this wrong. So there we go. You can keep experimenting with it to actually get a more natural frame rate or something you like. So that's it for car and pedestrian detection. These are actually pretty simple. So I hope you actually find this stuff useful, and maybe later on in the course I can add a lecture on how to actually create these cascade classifiers. Okay, thanks. Hi, and welcome to section 7 on face analysis and filters. So you saw in the previous section, we actually were able to use HAR cascade classifiers to quickly identify faces in an image. However, we didn't do much with those faces after that. Well, that's what we do in this section. We actually use some new libraries to do some complex facial analysis, and as well as apply some very cool filters, just like your favorite apps. So let's take a look at what exactly we'll be doing in this section. So we'll be using a new library called Dlib to identify facial landmarks in pictures of faces, which is pretty cool. Then after, we'll be merging faces together to produce sometimes scary results. And then that brings us to our 7th mini project, where we implement a live face swapper using your webcam, produce some very cool and again scary results. And then after that, we'll be doing our 8th mini project, which is a face reader. It can actually detect and count how many times you yawn. So that's pretty cool. So let's first talk about what makes face morphing or face swapping hard. So we saw it using HAR cascade classifiers with our face detection. We can simply cut someone's face out of an image pretty easily and quickly. However, if we wanted to make a face swapper between Hillary and Donald Trump, it would not work at all doing that method. It would just look horrendous like this. However, apps like Masquerade and Snapchat are doing some very advanced face swapping or adding very cool face filters here. And in fact, Masquerade, simply by doing face filters, was actually bought by Facebook for 35 million US, I think. So what makes this possible? So what actually makes face swaps or face filters hard is actually getting the images to align correctly. So what I mean by align, suppose we wanted to merge her face with her face. You would need to align these key facial landmarks highlighted here, eyes, nose, mouth, cheekbones, and eyebrows, onto her face. So we'd have to apply some warp perspective as well to actually get it to morph into her face properly. Now, in order to do this quickly, you're going to have to develop some sort of method that can actually identify these key facial landmarks quickly. And that's exactly what many researchers have been doing over the years. So the technique we're going to be using in this section was actually developed by two Swedish computer vision researchers, Kazemi and Sullivan. they developed this paper called 1 millisecond face alignment with ensemble of regression trees, which actually does facial landmark recognition very, very quickly. And you'll see it shortly. So if you recall, I said we'll be using Dlib to do some of our facial landmark recognition. Well, this method was actually built into the Dlib library, so that's what we'll be using soon. And I can show you some quick results of how it works. So this is Clinton's face overlaid onto Trump. It's pretty good, actually, and pretty scary. This is Donald Trump's face overlaid onto Hillary. Actually looks very realistic, but also very scary. So we'll be having some fun doing some more face swaps soon. So before we actually go ahead and install and use Dlib, I just wanted to reiterate what is actually a bit hard about doing this face swap here. So what's involved here is that first we have to identify the facial landmarks, which is what you saw previously here. And secondly, we actually have to now warp the new face onto the existing face. And then we've got to do some color matching. So we actually have to make sure the face lighting is correct here, which is why Donald Trump's face has a kind of bronzish tint here, yet it looks very similar to Hillary Clinton's face here. And then we have to create some seamless borders. So those are the edges where we've actually cut the face on. So it's actually looks pretty smooth in this picture and as well in this picture here. Alright, so actually now let's go ahead and install Dlib and start using it. So I'm going to quickly show you how to set up Dlib for use in Python. So firstly, let's visit this link here, SourceForge. So let's bring up that link, and that link is also available in the IPython notebook for lecture 7.1, available right here. So you download Dlib here, and version 19.1 is the latest version that's out right now. So once you have that file downloaded, you can unzip this file into this folder right here, and that brings it up this folder here. And now to basically create the bindings for Python, you just run this setup file here. So you just go, you click it and open it. It brings up that little terminal window there. Hope you saw it quickly. And that's it. Dlib is ready for use in Python now. It's actually quite easy. And the second part of the installation now is downloading the pre-trained model for facial landmark detection. So the next step is actually downloading the pre-trained model, and you just go to this link here, and that automatically downloads this file for you. And what you do with this file, you just place it in your default folder where your Python exe is installed. As you saw previously, you can just import sys and run some commands. I'm going to show you that quickly. So just run this sys.executable file here, and you'll see where your Python exe is installed. So you place that folder, that shape prediction model folder, landmark file, place that folder in that same directory where your Python exe file is there. And that's it. So once we do that, we're going to run some examples now using Dlib, and it's going to generate some facial landmarks just like this here. So we're about to do this in a few seconds. Just want to show you quickly what's happening here though, so you'll understand it in future. This landmark detection gives us 68 facial key points or landmarks. And what it does, this is the order here. So mount points are 48 to 61. You can see that here, starts at 48 here and goes all the way to 61 somewhere. And then there's right eyebrow, that's this range here, 17 to 22. Similarly for left eyebrow, 22 to 26, and actually this is a slight mistake here, it's supposed to be 21 actually. And similarly, the rest of the ranges here indicate different key points along the face here. So that's actually how this landmark detection works, and it gives these points here. So we'll use that in our future projects, but for now let's actually just start playing with Dlib, doing some simple landmark detection. Also, just want to note in future, in case this link ever goes dead, I've uploaded this file in my source files for this course. It's in the folder called Shape Predictor 68 face landmarks. So you can also access that file through there. Thanks. Alright, so let's go ahead and open the code for facial landmarks. That's lecture 7.1. And the first thing you'll notice here is that there's a copyright notice on this code. And that's because for this section here, I'm actually reusing some of the code that was available on Matthew Earle's GitHub and his website. He actually has a very cool and educational blog post about how you actually do facial landmark detection and merging of faces. So I do encourage you to visit his site and take a look at this. His tutorial is a bit more detailed than the one I have in this course here. However, I do try to make it simpler for you guys. So anyway, This is a copyright notice, so if you're using this code in any commercial project, just remember to keep this notice in the comment section of the code. And that makes us now ready to actually implement our face landmark detection or facial landmark detection. So let's go ahead and run this code just to see what's going on. And in a matter of seconds, we'll have identified yes. So it's the same picture I showed you in the presentation where we have President Obama, current president right now. And basically all the landmarks have been detected fairly well here. So lip, bottom lip, top lip, nose, eyes, everything seems to be in order. So that's pretty cool. So let's actually see what's going on in this code. So the first thing you may have noticed that's different is that we're importing Dlib here. So that's a must. We need to use Dlib in our code. So we have to import the package. And now we're creating a string variable here called predictor path that stores this string here, which is the name of our file, our model file. And then we're loading that model here. So we're creating our predictor object here and then creating our detector object here by calling dlib.shapePredictor, and we have the path for our predictor file, and then initializing our detector here. So now we have some classes here that are used for exception handling when we have too many faces or more than one face or no faces at all. So we have two functions here, as you can see, one called getLandmarks, and if you can infer, this function is basically going to get facial landmarks once we send an image into it. One thing you should note, I'm going to comment this code a bit more for you guys, so the actual file you might be seeing here in your files that you downloaded with the course materials will have a lot more comments that will help you step through this file on your own if you wish to do so. But I'm still going to explain this code without the comments for now. So what this function does here, get landmarks, basically it takes an input image, which is the image with the face we assume that has a face in it, and it runs the detector here that takes two arguments, one and the image itself, and gives you recs. And recs are basically is an array where we have faces that have been detected. So just the bounding rectangle of the faces again. And annotate landmarks is basically how we plot the numbers onto the face. So that's what the CV2 put index function does. And basically it actually also puts circles at those points too as well. And basically let's see what's going on here now. So we load our input image here, we get the landmarks using our getLandmark function here, and we then annotate those landmarks. So once we have our landmarks file here, which is returned here, and it's actually returned in a NumPy matrix array here, which this line may be a bit confusing. If you have some detailed understanding of NumPy and arrays, you would understand what's going on here. It's just the way we are reformatting our array that I could actually use now in annotate landmarks here. So we have our image and our landmarks, and then we're just plotting them here. So this function returns an image here, return IM here, and this image here does have all the landmarks in it. So quickly, and also we actually write this to our hard drive in case you wanted a hard copy of the file itself. So let's run it again, and there we go. So we have used this code here to identify 68 facial landmarks on faces. So now let's actually create something more complicated. Let's actually use this facial landmarks that we just extracted from that picture there to actually merge two faces together. So let's see how that works. Okay, so let's create our merging faces application. So let's load lecture 7.2 and bring it up here. As you can see, we still have our copyright disclaimer from Matthew Earl. And here's the code that we're using here. So this is basically his code. I've downloaded from his GitHub. That's somewhere over here. And I've actually made a lot of changes and edited it to basically suit our application here that we want to do, which is merge Hillary Clinton's and Donald Trump's face together. Okay, so actually let's run this code and let's see if it works and how it works. Okay, so here we are. Here's the first image. Let's bring it into view. So that's Hillary Clinton with Donald Trump's face over it. And here's the scarier one, I think. Donald Trump's face with Hillary Clinton's face over it. So that's pretty cool. And you can use pictures of any celebrities or your friends or your family. You can just go crazy and have some fun. So the second thing I want you to note about this code is that it actually is a bit complicated. It's quite long and sometimes quite mathematical as well. So I'm not going to explain this code in detail, unfortunately. However, what I'm going to do, all of these functions here and basically the overall process of what's going on here, I'm actually going to explain using these flowcharts here. So these 2 slides of flowcharts. It's not too difficult to understand the way I've shown it here. Optionally, you can take a look at Matthew Earle's website here, and I'll place the link in the IPython notebook file. He actually has a fairly good and fairly detailed explanation of what's going on here. Again, it's a bit mathematical and a bit tricky, however, it's definitely worthwhile understanding and reading this. So let's go back to my flowcharts and I'll give you a very high level explanation of what's going on. Okay, so let me try to explain how our face swapper app works. So we need 2 images here with 1 face in each image, and those are the faces that we're going to swap here. And what we do is that we use Dlib's face detector method here, this detector function, and what that does, which I didn't tell you previously, it actually fits rectangles using some algorithm to the face in question in the image. And then what we use those rectangles for is that Dlib's predictor function takes those rectangles, uses it as a bounding box essentially, because those rectangles would be different sizes and dimensions, and it converts those rectangles that fit to the face here to produce our facial landmarks. And it produces an array of XY coordinates, which are the locations of those facial features that you saw here in this Obama photo. So the next step, once we have our facial features or facial landmarks from each face image, we now have to produce a mapping between them. And if you remember correctly from our warp perspective and our non-affine transform generating functions in OpenCV, we actually need to now produce some sort of matrix here. This is the output here. This is a transformation matrix that actually maps these points together. So what this function uses, it actually uses a mathematical method called Procrustes analysis, and I hope I pronounced that correct. And what Procrustes analysis essentially is that it's trying to minimize a loss function to find this matrix essentially. So the next steps involve creating a mass, and we create this mass basically from our landmark positions, and the reason we need this mass for is so that we only alter the faces on the images that we want to swap. You can take a look of what the mass looks like, going back to Matthew Earle's blog. This is basically what the face mass looks like. And then the next step involves actually blurring the edges of the mass so that we have a smooth transition from the newly transformed face onto the other face. Okay, so once we have the mass, the next step is basically to use the transformation matrix M that we got previously here. And we use that matrix to produce a warped image of the face for image 2. So that's assuming we're trying to get a mapping from face 1 to face 2. This transformation matrix actually transforms the face so that it fits perfectly on the face on image 2. So once we've executed the warping of image 1 onto image 2's face, we then have to generate a combined mass. And to do this, we take image 1 and its facial landmarks and the warped mass that we just produced. And we produce this combined mass, so that we ensure that the features from image 1 are covered up and the features in image 2 show up in the final output image. So what I'm saying here is that we basically ensure that the face, like say we're putting Hillary Clinton's face onto Donald Trump, we're showing his face is covered up and her face is visible. So the last step now is color correction, and that's how we attempt to match the skin tone and lighting, as you saw previously how realistic it looked when we put the faces on top of each other. That's what we do here. So that's what our correct color functions does. It takes these input arguments here and produces a color corrected warped image of the face in image 2. So that's quite cool. So I said this was the last step. It's actually the last step in producing all of these things you need to actually generate our face mask. But the actual last step now is actually doing some image arithmetic that takes the face from the first image and adds it to the warped and color corrected face of image 2. So now let's return to the code and see how it's done there. Okay, so we're back at our code. So let's take a look quickly at what's going on here. So you can see firstly we have defined some parameters here. However, these are actually just lists defining the different facial key points here, or landmarks. And then we've combined them into this align points array here. Similarly again for the overlay points. Then another parameter for the color correction. That's be used in our color correction function somewhere here. Here it is. And these are our classes. Well, we load our predictors as we've done previously. and pointed it to the correct directories. We have our classes that handle the exceptions. We have our getLandmarks function, which is the same as before, similarly for our annotated landmarks. And now we have some new functions here, which I may have mentioned previously in our flowcharts. So we have our draw convex hull, which I don't believe I mentioned, but you remember what convex hull was when we looked at contours. We have our getFaceMask function here, which generates a mask for an image. Then we have our transformation from points, which you remember computes it using the Procustes method to produce a transformation matrix mapping the landmarks from one image or one face to the next. Then we have our function here that reads the image and gets our landmarks. So it's a simple function right here. It just resizes the image to make it processing faster. So then we have our warp image function here, which actually warps our image mask according to the matrix M. And this is the shape of that matrix itself, or that image, I should say, and gives us the output image here. Well, the output mask that has been warped using CV2 warp affine. And next we have our correct colors function, which actually tries to match the skin tone and lighting conditions between the two images. So it's a pretty cool function here. You can experiment with it as well. And then that brings us to our main swappy or swapping function, which I named swappy for some reason. Okay, so let's see what's going on inside our swappy function. So as you can see, it takes two images here. Those are the images that we have the paths entered to here. So that's Hillary Clinton and Donald Trump. And it gets its landmarks here. Then it computes the transformation matrix using those landmarks. Then we generate the mask, then the warped face mask, then the combined mask. And then we have our warped image 2 mask, and then color corrected warp image 2 mask here. And then it combines the masks in our arithmetic operations here. And that's how we get our face swap. So it's actually pretty simple here when you look at it. So what I've done here too, is that I'm actually creating a face swap with image 1 over image 2, and then image 2 over image 1. So let's take a look at it again. There we go. So image 1 was Hillary Clinton. So by when you run image 1 here, you're keeping this in the foreground, or the background I should say, and putting Donald Trump's face over this person's face here, which is Hillary Clinton, and vice versa for the reverse order here. So that's our pretty cool image or face swapping app here. I invite you to go crazy, try your friends, family, or spouses. Just create some very cool, but don't blame me if you create anything too scary. It's not my fault, it's our code. So have fun. We're now going to create a live face swapping app. So what we're going to do, one of these images here is actually going to be fed live from our webcam, and the other image here can be any person you choose. It can be Donald Trump, Hillary Clinton, Kim Kardashian, whoever. Let's have some fun. Hi, and welcome to our 7th mini project where we're going to make a live face swapping app. So this app is actually going to be just like the popular Masquerade app, or MSQRD. And this is a screenshot of what we've done here. So this is Donald Trump's face overlaid onto my face, and it's actually working in real time, which you'll see very shortly. Okay, so let's go ahead and load our code for lecture 7.3. That's our 7th mini project. Okay, so here we have our code. So first we have a copyright from Matthew Earl. And now here's our code. And the code should look very similar to the one you saw previously. It's actually very similar. However, the key differences here is that previously we were swapping a face from image 2 onto image 1. Well, in this case, our image 1, which is our base image, is actually taken from our webcam. So we do our standard webcam initialization, capturing the frames here. We are slightly reducing the size of the frame by 75% just to increase processing speed, or reduce processing time. I should just write that in here. And we're just flipping the image here so it's more mirror-like, and then passing it to our face swap function, which is very similar to what we've run before. So again, the differences here is that frame is our image 1, that's our image captured from the webcam, and filter image is basically the filter or image 2 that we want to place onto image 1. So in this project here, we're putting Donald Trump's face onto anyone unlucky enough to be in a webcam view. Okay, so there's a couple little things I would like to show you that's different in this code. Firstly, you may have noticed I have a parameter setting called Dlib on. So why would we want to turn Dlib on and off? Well, that's actually what we're doing in this function here, getLandmarks. And what I'm doing here, I'm basically telling this function here whether I want to use Dlib to do the face detection or whether I want to use har cascade classifiers. And the only reason we actually use har cascade classifiers sometimes in this code here is because it's actually a lot quicker than Dlib in face detection. We still, however, use Dlib for actually picking up and detecting the rectangles once a face has been found. So if you run this code with Dlib on and you find that the frame rate is actually a bit slow, then maybe just try turning Dlib off here and you would probably see a slight boost in speed. So just set this to false if you want to turn it off and use har cascade classifiers instead. Okay, so there's a few other things I'd like to show you in this code. So this is our face swap function here. This basically takes our image here from the webcam and our filter image, which is Donald Trump, and actually does the full face swapping here. But what we do here, we actually write the image to our hard drive and then reload it here using imread. And we do this simply because it's the easiest way, or probably one of the easier ways, just to get it into correct output. If you were to load this or return this image directly here, it actually would not look in the same format that you actually think it would look. It's a bit messed up, so we actually need OpenCV to write it as a JPEG and then reload it as an image here, just to clean it up. And then we enlarge it here, resizing it. So even though we shrank it here, we're just upscaling it here just to return an image that's a decent sized image again. And I think that's all the major differences in this code. I don't believe there's anything else that's different. It's pretty much the same thing we did previously. So now let's go ahead and run this code and see our very cool live face swapper in action. Okay, so let's get ready to run our code. So be prepared to have your mind blown, I hope. Okay, there we go. Just ignore this warning. Alright, so here I am, looking like Donald Trump. So as you can see, Dlib's tracker actually works pretty good. Frame rate isn't too bad. Seems to be like maybe 5 to 10 frames per second. It's pretty smooth, keeping track of my face. If I put my hand up, yep, disappears. And you can see I've printed some error messages here every time that happens. No or too many faces. So that's pretty cool. Let's close it off there. So let's try this now being false here and see what difference that makes. Okay, let's bring it up. Okay, so to me the frame rate does seem to be similar, although it does seem to be slightly faster. Performance tracking is roughly the same, so that's pretty good. As you can see though, Dlib actually does have an issue with keeping track of my mouth, because I'm actually moving my mouth here. I'm not talking like a mime or something. But however, you don't see my mouth moving. Right now Donald Trump's lips are fixed here, so it's very unnatural looking when I'm talking. However, if I do open my mouth like that, it does sort of track it there. So this is pretty cool and pretty nifty. Alright, so I invite you to try some other cool celebrities. We can actually try Kim Kardashian now. So let's go ahead and change our name to Kim Kardashian right here. Okay, so let's go ahead and change this to Kim. And the picture I'm using is a picture of her face right here. It's no better picture than this, I believe. So let's go ahead and run this code. Oh man. Yeah. This looks pretty good, doesn't it? Well, you can keep experimenting with different celebrities. You can try all sorts of different pictures. This is actually just pretty fun though. And it's actually pretty cool that we made this in Python just by using Dlib's library here. So again, have some fun, knock yourself out and just go crazy. And maybe even scare your friends a bit, because I actually did scare some people with this. So enjoy our live face swapping app. Thanks. Hi, and welcome to our 8th mini project, which is a yawn detector and counter. So what this app does, it basically keeps a live track of your face using our webcam, and it analyzes when you yawn, and as soon as you do, it increments our counter here. So how we do that is by keeping a live track of our facial landmarks on our subject, which is myself here, and in particular we're looking at the mouth facial landmarks here. So as soon as we detect some large separation between our upper and lower lips, we basically just increment this counter and indicate below that our subject is currently yawning. So let's go ahead and open our code. That would be lecture 7.4 or 8 mini project. which I have entered mini project twice in the name here for some reason. Okay, so let's take a look at this code. Basically, we're following the same pattern of code using Dlib and all that stuff. However, actually we're not doing any phase swap, so actually that's why our code is much shorter. And what we're doing here, we actually have some functions here where, like this function here called toplib and bottomlib. And what these functions do, it basically uses the landmarks that we generate from our getLandmarks function here, and it basically extracts our toplib from our facial landmark numbers here, which, as you know, let me just bring this up in our presentation file. Not this image actually, I'm looking for the one with Obama. Yeah, so we can see in this image here, our mount points lie between 48 and 61. However, you can see there's distinct numbers that we use here, this range here and this range here, to indicate toplib and bottomlib. So let's go back to our code. So that's what we do here. So in this range here, for range I in range 50 to 53 in our landmark matrix, or array I should say, we're just appending those positions to our toplibs array here. And then what we're doing, we're storing all that information here, those are the XY coordinates, and just taking the average of those coordinates here. So imagine we're averaging out the positions here. However, if you're looking at toplib and bottomlib, assuming no one has like a horizontal face position in our webcam app, we basically only need the Y coordinates here, because the Y is basically indicating the vertical range here. So let's go back again to our code. And so that's what we're doing for the toplib and bottomlib functions here. So I should just say this isn't the most efficient use of code, because the only difference is here is different numbers in a range. However, we are reusing a lot of code here. So just don't consider my code to be the most elegant and useful right now. And then what we're doing after that is that we're actually using a function called mountOpen, which basically what it does, first it gets our landmarks, and if there are no landmarks in an image, it returns an error. And I should have said equals to an error from, this is the top part of it here. That means if it gets more than one face or no faces in our image, then we get an error here. And what we do, we return our image, just returning it back to the function, doing no processing, and returning the distance between our top and bottom and toplib is 0. So that's exactly what the rest of the lines in the code do. It basically gets the landmarks, gets the center position, the vertical position of the toplib, then the bottomlib, then calculates the absolute distance between them, and then basically returns the image with our landmarks, which we'll be displaying here. That's this image, as you've seen before. And then also it returns the distance between the toplib and bottomlib. And it's that distance here, which is if it's greater than 15 pixels, greater than 15 pixels here being constituted or classified as a yawn. And I should say that 15 pixels is what I use as a hard-coded value based on my webcam's resolution and the distance I sit from my laptop. However, if you think about it, it probably should be a proportion of our head frame, so a percentage of our head frame. So you can probably say if it's greater than, say, 5% of the vertical position of the head is extracted from the frame, then it's a yawn. But you can play with this value and experiment. It should work in most standard laptops, because I believe I have a 1 or 2 megapixel webcam. I'm not actually sure. Actually, I think it's 480 by 680 in video capture mode. So that's actually a VGA resolution. So anyway, once a yawn has been identified here, once it reaches this threshold, we change our yawn status here, which is a variable we set to false by default here, and I'll count to 0, to true. And then we simply display our subject is yawning on our screen. That's what you saw in our image in the slide earlier. And we also display our count. So our count starts at 0, so as soon as it's counted here, we increment it by 1. And we display that on our image itself. However, if no yawn has been detected, we basically keep our yawn status at false here. And basically this previous yawn status just as an update field, so that we don't double count or keep counting wrong. You can experiment a bit if you want to try some different things. And in the end, what we're showing here is our live facial landmarks and our yawn detection frame. and we press enter to exit this program again. So let's run this code and see how it works. Okay, so our code is up and running, and apparently while I'm talking here, yawns are being counted, but let me just stay silent for a minute, well, for a second, and make a yawn. So let's try this. Good. You see everything is off right now. So maybe that 15 value is too sensitive. Maybe I'll try it at 20 next time. There we go. Alright, so this is pretty cool. Let's exit this. Let's actually try making this value at 20. See what happens. Okay, so I can talk a little more freely now with it without false positive yawns being identified, although we just got 2, 3, 4. Definitely one there. In fact, let's make this 25. Let's make it a little more resilient too. As you can see, you may have some manual tuning to do, which is why I said you probably should make it a proportion of your face image here. Okay, so I'm looking pretty stupid doing this, but it's actually working pretty decently now. Less false positives in our image, although we just got one. But that's pretty cool. So you can actually play with this. Going back to this one more time, actually something I want to mention. Did I run this? Yeah, here we go. Okay, so you can do a lot of cool things by knowing your facial landmarks here. Things like emotional analysis or smile detection, or whether you want to just do anything cool with faces, like facial analytics for attractiveness or face shape. You can use these facial landmarks to calculate those things. So this is actually a pretty cool thing to do. So, and you can actually just try to find like lines and gradients with these points here. There's so many powerful things you can do with machine learning as well by having this data. So this is a pretty cool project to do. And actually, I just mentioned machine learning, and we're actually moving on to the next section now, which is machine learning. So cool. So let's end this here and finish up with this, which we're actually finished with this code here. So I hope you enjoyed this project and the other projects in this section. I think it was pretty cool, and I had a lot of fun making this section. So let's now move on to the the 8th section now, which is machine learning, where we actually do some handwriting analysis for handwritten digits, and then we actually start using OpenCV for some facial recognition. So that's going to be pretty cool as well. Hi, and welcome to section 8, where we take a look at machine learning in computer vision. So in this section, I'm firstly going to give you a brief overview of machine learning, and then discuss how machine learning is used in computer vision, and then we'll go through a very simple machine learning algorithm called KNNs, that stands for K nearest neighbors, and then we're going to go straight into a 9th mini project, which is recognizing handwritten digits, and then our 10th mini project, which is face recognition, which can actually be used to unlock your computer, which is pretty cool. So what exactly is machine learning? I mean, machine learning has been all the rage recently in the computer science world, and deservedly so, because machine learning actually enables computers to act somewhat intelligent. So basically, machine learning can be defined in one line by just saying it gives the computers the ability to make predictions or learn from data. Some examples of machine learning use cases today are in stock prediction, predicting sentiment in tweets, predicting illnesses on your medical data, or perhaps using your past shopping data to predict your future purchases. And perhaps the most popular example of machine learning is in email spam filtering. So essentially, there are two core types of machine learning. There's supervised and unsupervised learning. There is actually a third type called reinforcement learning. However, it doesn't have much applications in computer vision, so we're not going to discuss it here. So let's get into supervised learning. So essentially what supervised learning is that we give our supervised machine learning algorithm some input data along with some correctly classified data. So think of our spam filter. Let's say we gave our supervised machine learning algorithm 1,000 examples of spam emails and 1,000 examples of non-spam emails. Our algorithm basically then uses that input data with those labels to form some sort of mathematically defined decision boundary, so that when it receives a new email, it actually uses this algorithm it developed inside here to predict whether that email has been spam or not spam. So what about unsupervised learning? Well, the main difference here in unsupervised learning is that we don't give it any ground truth. We just have input data and we feed it to our unsupervised machine learning algorithm. So think of it as clustering. Think of it as trying to find patterns in data. So in this example, we have some input data of basically food types or food ingredients here. And we can imagine an unsupervised machine learning algorithm looking at different attributes of each thing here, of each data item here, and then determining that there are two clusters of food ingredients here, which will essentially be meat and flavors. So this is some examples of supervised and unsupervised learning in computer vision. So here we have our labels for our handwritten data set here. So you can clearly see we have input data and then correctly labeled data here. And for unsupervised learning, this is just an example of an unsupervised learning algorithm at work here. These are screenshots I took from Google's image search. So when you search for city, these are the related images you get, similarly for snow and mountains. So you can sort of see that Google is actually kind of clustering types of images here so that it knows. However, just so you know, Google actually does a lot more and more in-depth image searching stuff than this. They're actually doing scene labeling and object recognition, which is pretty cool, and that's how their image search has gotten so advanced recently. Getting back to the topic at hand, machine learning in computer vision. What is it good for? Well, it's so many things. It's actually good at facial detection, face recognition, which is our 10th mini project, classifying types of cars and images, road sign detection, license plate recognition, signature verification, and so many others here, especially in robotics as well. And our 9th mini project, which is what we're going to do next, understanding handwriting. So you can definitely see that machine learning is actually on the forefront of computer vision research right now, and it's proving remarkably effective and useful. Okay, so you've seen those examples of machine learning in computer vision, but how exactly do we use an image or image data to predict? So there are many ways actually. Firstly, we can do something simple and look at the raw pixel intensities here. However, as you can see, this is a 20 by 20 image here of a pixel of a number 1 actually. And if you were to keep feeding in this continuously into machine learning algorithm, this would be a lot of data for characters. So it's probably not the most efficient way to do this. So another method we can do, which you've seen before, is using key point descriptors. So things like sift, surf, orb, etc. Also, we did look at histograms of image gradients, hogs, and hogs are actually very good and very condensed descriptors of images as well. Similarly, you can actually look at pixel statistics, which are like pixel dimensions, mean, variance, and many other attributes as well. So that's exactly how we do some basically feature engineering from images, and then we feed those features that we extract into our machine learning classifiers. Alright, so you're now ready to start learning about your first machine learning algorithm, and the one we're looking at today is K nearest neighbors, that's KNN. So KNN is pretty basic, it's pretty easy to explain in a couple minutes, and essentially what's important to remember with KNN is that it classifies new data based on how close it is to existing data. So this single slide basically summarizes how KNN works. You don't actually have to read this wall of text here. I'll just step through it verbally here for you using my mouse, and hopefully you get the gist of how KNN works. So imagine we have labeled data, which are these green dots here, and they all belong to the green class. And then there's these red balls here, which belong to the red class. And intuitively we can see that basically this dotted line here is our intuitive decision boundary line that separates green from red. So what if we get a new data point here, which is this blue ball here, and we don't know yet what he is, or what class he belongs to. So what KNN does, and this is where the K in KNN stands for, it looks at the K nearest neighbors. So let's first assume we're looking at K being 1. So unfortunately, if K is 1, the nearest neighbor to this blue ball is actually this green ball here. And unfortunately with that means that this ball will be labeled into the green class, which is wrong. And this distance metric we use to measure the distance is called Euclidean distance. and Euclidean distance is pretty much used in KNN to actually weight the distance itself. So now, what if k was 3? Let's see what the 3 nearest neighbors are. So let's assume, this is what I'm stepping through here now, the distance between the blue and the green here was equal to 2 units. And the distance to the second nearest neighbor, which is red 1, let's call this red 1 here, is 3. And let's assume the distance between the third nearest neighbor, let's assume it's this one here, that's red 2, is also 3. So now, using the weighted distances, remember the distance is 3 for here and 3 for here, we can determine that the overall distance from the red classes, using k equal 3, is 1.5. However, the distance between here and here was actually less, it was 2. However, there was only one green ball that was here. So it would be 2 divided by 1, essentially, which is equal to 2, which means that the distance here between the red balls is actually smaller. So using k equal 3 in this case will give us that the blue ball belongs to the red class. So just one obvious thing here. It obviously would be good to have k be a large number. However, you don't want to keep working out these distances all the time for new data sets. So you sort of have to optimize your value of k that works pretty much good enough. And also take into consideration the fact that suppose you had only 2 or 3 green balls and like 100 red balls. Setting k as a large value would actually obviously always skew your new data sets to be the one with the bit larger amounts of data. So those are some weaknesses of k nearest neighbor algorithm. So we're now going to go into our our 10th mini project, which is the first in this section, which is on using KNN to actually classify handwritten digits. So it's going to be pretty cool, and I hope you find it very informative and useful. And welcome to our 9th mini project, which is the classification of handwritten digits. So what we're going to do, we're going to take an input image here of handwritten numbers and use machine learning to identify what each of these numbers actually are, giving an output of this. So before we get into the code, I'd like to describe the dataset that we're using to train our classifier. So this is the digits file that's supplied in OpenCV. It consists of 500 samples of numbers or digits between 0 and 9. So it's set up in an order where we have 100 columns here, 5 rows each, and it's 50 because it's 10 by 5. So this is the order. So this is the dimension, of this image here. So let's talk a bit about the dataset again. So we have 500 samples of each number between 0 and 9. So that's a total of 5,000 image samples here. So these are 5,000 screenshots or snapshots of numbers here. And each number, each character, is actually 20 pixels by 20 pixels here. And they're all in grayscale with black backgrounds. And the image itself is in white, as you can clearly see. So obviously using this data requires some data prep, and that's what I'm going to talk about now. So as you saw, we have 500 samples of each digit with 5 rows of 100 samples each. So what we then need to do, we need to basically arrange this data in a NumPy format array. So you'll see this in our code, but what we essentially do, knowing that each image here, each character is 20 by 20, we basically create a NumPy array that's 50 by 100, and these are the third and fourth dimensions here. So these are essentially the pixels itself in the image. So we have a matrix that's 50 columns by 100 rows, and that they have 20 layers, and then there's 20 layers on top of that, and those are just the image pixels itself. So yes, that obviously is confusing when you're talking about multidimensional arrays. So what we do with this part of the data here, the 20 by 20, is that we actually flatten that array. So imagine now, let's go back to this image. There's 20 rows here and 20 columns here. So imagine now that we take each row one by one and we put it next to each other. So pretty much like this. We have the first row here of data, and it's 20 pixels, as you can see here. But imagine we take the second row now and we just append it to the same row here. So what we do, we create a row that's basically one row with 400 columns here. So that's basically what we call flattening this image here. So this image no longer is a 20 by 20, but a 1 by 400. So that flattening is actually what I mentioned in this line here, creating a 1 by 400 row from a 20 by 20 pixel array. So you may have seen that I've mentioned we are splitting the data into two segments here, 70% for a training set and 30% for a test set. If you've never heard these terms before, you may find this concept a bit strange. However, in machine learning, it's quite important that we split our data sets into a training and a test set. And the reason we do that is because, let's say 70% of our data lies in this portion here. That's this left portion here from this line. And how we basically fine-tune our model is that we train our model on 70% of the data here. So we feed this to our algorithm, it develops a model, blah blah blah. And then how do we evaluate the effectiveness of that model? That's what we use a test data set for. That's why having a test data set is very important. So this remaining 30% of our data here is what we essentially use now to test our model. So we've trained it on 70% of our data, and then we now want to see the percentage in terms of accuracy on the test data set here. So that's how data scientists and machine learning guys, that's how they essentially train their models. So I hope that explanation of our data preparation was clear. If it isn't, just message me on Udemy, and I will try to reply to you as soon as possible. So now that we've gone through our data prep, let's now step into the code and actually see how we can use OpenCV's KNN function to start classifying our own handwritten digits. Okay, so let's go ahead and open this code. It's lecture 8.2, mini project number 9. Okay, so here we go. So you'll notice there are 3 blocks of code here. And essentially though, the first block of code is actually doing the bulk of the main processing here. What we're doing here, we're doing our data prep, training, and evaluation. So let's go ahead and run this and see what happens. So there we go, it loads our image. This is the same data image you saw in our presentation previously, our digits image, I should say. And now it's done. We've actually we actually split our data set into 70% for our training data set here. Our test data set is the remaining 30% here. And we've actually tested our model on our test data set already here. And we've gotten an accuracy of 93.47%, which actually isn't too bad, especially for a classifier that trains in a couple of seconds. So let's take a look at briefly at the other sections of the code. So you may have remembered that we're actually taking an input image here and using the model we just trained to identify these digits here. So that's what the remainder of this code is. How do we now load an image in, a fresh new image of handwritten digits? How do we extract those digits there using maybe fine contours perhaps? You'll find out soon. And then once we've extracted our handwritten digits from our input image, we then feed it to the model classifier that we created in our first cell block here. And that's basically what's going on here. So there's actually a lot going on in this code, and I maybe will not explain everything in detail. However, I will explain the core functions that's going on here. I do invite you to go through this code line by line on your own, because there's actually a lot of important and useful stuff going on here. So let's quickly go line by line through this code. So firstly, we load our digits image here. That's our data set. That's our raw data set, I should say. And then I'm just using pyramid down just to rescale it to smaller. I'm also converting this into a grayscale image because it loads by default as a full color image. And then this is what we're doing here. Remember previously in our slides we said we reshaped the data set into a 50 by 100 by 20 by 20. 50 rows, 100 columns, and 20 by 20 was the pixel dimensions. Well, we use NumPy to split it into this form here. So we take this image here, which is gray, and through NP's horizontal split and vertical split, we're able to cut this array into an array of this dimensions here. So this is the list cells, and then we convert cells into a NumPy array here, and we just print the dimensions so we can check it as we test our code. The next set of lines here, train and test. This is essentially where we split. We do a vertical cut in our data. So we get 70% of it being used for the training data set. And just so you know, training data sets, if you're splitting data, you should always use the majority of data to train your model first. So no lower than 70% typically. And at the same time, we're using NumPy's reshape function to actually flatten that 20 by 20 array here into a row, or it's 1 by 400. And we're doing it for both test and train. So our size of this dimensions of this train and test arrays now are 3500 rows by 400 and 1500 rows by 400 as well. 400 being columns on both. So now we have to create our labels. So we can easily create our labels here. We know the order of our image here. Let's just bring this up here. It goes from 0 to 9. So we just quickly create k, an array of digits from 0 to 9. And we repeat them using NumPy's repeat. So we do it 350 times because this is a group of 10 numbers here. And so then we just append this array here to our axis. So once that's done now, we can actually now initiate our knn object here in OpenCV. So the command to do that is basically cv2.knearest, and we give it a name, so that's knn, and then we use the method in knn to train. So we feed this knn training algorithm our training data, which is this here, as you remember, and we give it our training labels, which are this here. And then simply we just use the find nearest, which is the another knn method, and we use tree. Remember, we previously used tree in our example, and you can technically use any number you wish. Probably not use 1, but tree to any number is fine, just not too big because it slows down the processing time here. And what's important to see is that knn find nearest returns these 4 variables here. So simply ret is basically true or false if it successfully ran. Result is actually important, and we'll use result to actually calculate the accuracy afterwards. And neighbors, basically that's the neighbors for each line, and distance. So you don't necessarily need these two unless you're analyzing individual data to it. So let's see how we calculate accuracy now. So matches would be equal to how many times the result was equal to our test labels. So that's basically a very quick, nice line in Python that we can just compute how many matches did we get. So now that we have matches, we can use this line, np count non-zero matches. So this basically counts how many matches weren't true in the statement here. So that's how we get our correct matches and our number of matches as well. Sorry, number of matches would just be the true or false of this statement here. So then that's essentially how we could calculate our accuracy now. So we have how many were correct here using np count non-zero matches, and we just find the percentage here, result.size, size giving the total number in result itself, and that's quite simply just getting the accuracy as well as a percentage. So that gives us 93.47. Let's run it again, and there we go. So let's just do a quick experiment with k equal 1. Let's see how accurate that gives us. So you can see it's 93.27. It's actually pretty good. Let's try k equal 5 or 6. It's actually went down. So you can see, you can actually play with this, or you can just run a loop and test different values of k, see what gives you the best value. So I think k equal 3 gave me the best value between k1 and 10. So let's use k equal 3. And now let's step down into the other functions now. So let's scroll down here. Now I should say these functions here are basically needed to basically process the image, the input image here. So we've got functions like xcode, that's left to right sorting. Hope you remember that from our contour section. We have a pretty bulky function here, which probably is not the most efficient code again by me, but this function basically takes a contour that you have extracted or cropped and makes it into a square image. So it probably adds some padding, well it actually does add some padding to that image, and then resize to pixel, so we can just resize it to a pixel dimensions that we input here. So it's probably not necessary, but I think the reason I built this function was to add specific shades or colors of pixels to the image as well as keep that image centered. So we'll use these shortly, just going over it quickly. It's not too important, but you can play with them or create your own functions that may be much more efficient than mine's. And this is the bulk of the code that processes the new images. So let's go back to our presentation here. This code essentially takes this input image here, finds our contours, extracts our contours, and processes it, and then feeds it to a classifier. So let me scroll down to the pipeline that we're doing here. So rather than go through the code, which I may lose track of you there, because it's kind of boring and a bit tedious sometimes, I'll show you this pipeline here, of what we're doing. So let's take our input image here. So we first grayscale it here, then we apply some Gaussian blur, and then after we find canny edges. And as you may remember from our section where we found contours, applying canny edges actually helps find contours actually get necessary or the correct contours that we actually want. Unlike if you didn't do canny edges, you would probably pick up a bunch of noisy contours in this image. So this is a good way to clean up images before using it into fine contours. So then after that we extract our contours. So these are the contours that we get basically from running fine contours on canny edges here. So we get these pretty nice contours here. And then afterward we get the bounding rectangle for each contour. So you remember what convex hull was? Well, bounding rectangle is pretty much a similar thing. It just gives us the rectangle dimensions around our contour from the max and min, etc. here. So then once we do that, we actually filter our contours. And what do we mean by filter our contours? Well, what if we picked up some noise here? What if there was because someone had a little scratch here, whatever? Basically, by filtering our contours, we can actually remove tiny small contours that don't belong here. So we only pick up the ones that are clearly digits here. And once we do that, we crop these digits out here. So this is what this line does here. We crop it out and then we actually blur it even more. So we add some blur so to remove any jagged edges we have here. And then we threshold or binarize our image and then make it into a 20 by 20 square. So here we are. And we threshold it just to change and we do probably an inverse threshold I should say. That actually gives it a black background and a white foreground. And then again we convert it into a 1 by 400 array, which is the input to our classifier. Because you remember each data line or data row, when we trained our classifier, was a 1 by 400 row. That constituted the 20 by 20 image. So that in a nutshell is exactly what we're doing here. So let's go back to our code and just quickly take a look at what's going on again. So as I said, these are our functions I defined. I'm not going to go through this in much detail. However, it's a good exercise for you to go through these things on your own. So this one makes an image a square and this one resizes it to certain pixel dimensions, which is 20 by 20 in our case here. So let's just step through this quickly and see what's going on. So I left some of these things here in, that's commented out, but you can actually, let's not comment it out, let's keep them in, and we can actually see each step as I showed in our pipeline over there. And then this is where we filter our contours. Remember, if you're using OpenCV 3.0, remember to keep this here, because the third argument is going to return an error if you don't have it in. So then we sort our contours left to right by our x coordinates using this function here, because we want to actually retain the number in the sequence that it was written in. So this is our array to store the numbers itself. So we go through each contour that we got here, and basically we get our bounding rectangle again and we crop it out. And this is here where we filter contours. So once the contour has a width that's greater than 5 and a height that's greater than 25 pixels, we pass it into this processing here, where we then feed it into a classifier, which is done somewhere here. Where is it done? Right here in our code. Okay. So this line essentially acts as a filter for our contours. So here we crop the contour itself, then we threshold using inverse threshold, so we get the black background, white foreground. We use our function to make it a square, then we resize it to 20 by 20 pixels specifically here, and this using the squared image in it, and we show our image before passing it to our classifier right here. So then this is where we actually reshape or flatten our image here, because in this form it's 20 by 20. Now we need it in a final array form, which is 1 by 400, and we convert it into the data type that actually we need to feed it into find errors here. So that's what this line does here. It's a good data type conversion to float 32, and then we simply pass it to our k-nearest neighbor algorithm here, and then we just convert the result, which is what we got here. Our result is actually an array, so we need to index the first element of that result here. So this looks a bit silly here. We're converting result from a float to an integer to a string, but unless there's an easier way to do it, this was surprisingly necessary to convert it into the number we want, like in this format here. So then we just append it to our number array here, full number, and we also display it on the image itself. So using some of those dimensions from the bounding rectangle, we know exactly where to put the text in our image, and we just add the text a bit here with plus 55 pixels, just so it doesn't go over our image itself, our number itself. So let's go ahead and run this code and see it in action. Okay, so as I said, we're going to look at each processing line here. So this is our initial image, this is our grayscale image, this is our blurred image here using Gaussian blur, our canny edged image, and it's tiny. Let's bring it into view here. This is a tiny image here. So this is our image here that's cropped out, inverse thresholded, blurred a bit as well, and resized to 20 by 20 and also made square. So it's 1, 3, 5, 4, and 0. And as you can see, even though it's tiny, it actually looks a lot like a digits dataset, which is our aim exactly. We need to basically get our input data that we process from our original image here. And this isn't our original image, this is our classified image. I'll just hide this for now, hiding the surprise. So but what I was saying is that we need to get our input data to look like the training dataset that we used. Okay, so let's actually run this again and bring up image here. So I actually want you guys to see the classification being done live here. So we step through. So we fed that one that we extracted, that tiny one here, to our classifier. Then we feed the 3 to it, then the 5, then the 4, then the 0. So that's pretty cool. I should say that using this KNN stuff, even though I've done some pre-processing of this data here, it's not terribly accurate. Generally on my real life data it's about 80% accurate. You can try experimenting with it as well. I'm pretty sure the issue why it's not being 100% accurate is because this process here where I'm prepping the data to look like the input image still isn't exactly like the input image as well. And secondly, well probably more importantly, k-nearest neighbor isn't the most accurate algorithm here. 93% accuracy is actually not good on image datasets. I should say datasets of handwritten images or digits. There's a dataset called the MNIS dataset that has, I believe, 60,000 samples of handwritten digits. And researchers all over the world have gotten close to 99-point-something% right now using convolutional neural networks and variations of it as well. So I invite you to actually challenge yourself and start playing with the MNIS dataset. Hi, and welcome to our 10th mini project, which is on facial recognition. So we're going to build an app that's basically trained to recognize your face and your face only. And you can actually use this app to unlock a device like your computer. So that's going to be pretty cool. So before we dive into the code, I just want to explain some brief theory about facial recognition. So facial recognition is actually a form of machine learning, and you'll see we'll be applying some of those machine learning principles in this mini project as well. So this is an example of a very bad facial recognition system. It's clearly not George Bush. But surprisingly, some animals can even do facial recognition. Dogs, crows, and sheep can do it to a degree. So before we dive into the code, I'll just briefly explain an overview of how facial recognition systems actually work. So at a high level, all facial recognition systems follow these 3 steps. First, we have to obtain and normalize our faces. Normalization is a process where we try to become invariant to lighting conditions and alignment issues. And then once we have our data set of faces, we then have to basically extract features from those faces. So these are some different feature extraction methods. We're actually going to use this last one in our project here today. But remember previously, we could have actually extracted landmarks. Remember those landmark features and their locations? Those were a form of features that we could have extracted from faces. And then we essentially have to train our model using these features. And then in order to classify features or faces, we then feed our faces or a new face into that model, and which will then return a confidence or probability value that this face is you or someone else. So fortunately, OpenCV actually comes with 3 facial recognition libraries, and they all operate pretty similarly. However, today we're only going to use histograms of local binary patterns, and this is actually the best method for facial recognition in OpenCV. Both eigenfaces and Fisher values, they don't seem to be as discriminatory as local binary patterns. So let's briefly explain each at a high level. And because these are all quite technical, explaining each in detail is beyond the scope of this course. However, I will discuss some of the key points of each method. So first, starting with eigenfaces. Eigenfaces uses a technique called PCA, or Principal Component Analysis, which reduces the amount of data necessary to store key information about a face. It does this by taking into consideration the features that account for the most variance in the image. Also, Fisher faces uses a similar method called LDA, which is Linear Discriminant Analysis. which also takes into consideration the class labels as well as the data when reducing dimensionality. And finally, the one we'll be using in our example here today, local binary patterns. And this works by extracting local features from segments of the face. So imagine segments or areas of the face being like the positions of the eyes, nose, and ears. And what it does, it preserves these spatial positions. And basically what it does when it's trying to classify a new face is that it compares these positions to the new face as well. So it's actually looking at local areas of your face and matching it to the new face. And it then gives you a probability or confidence level of that face being the face it's trying to match. So you've got a high-level understanding of how facial recognition systems work. However, before we dive into the code, I'd like to basically go over the flow process of what we're doing in our code. And that's a two-pronged process. We basically are collecting data and then we're classifying new faces. So starting with training data first, we use hierarchy cascade classifiers on our webcam images to collect 100 images of your face. And we then normalize those images by grayscaling and resizing to 200 by 200 pixels. And then we attach an array of labels, and those labels will just be yourself, because there's only one person we're training this for. So now when classifying a new face, we similarly extract it from the webcam, follow a same normalization process here, and then we just pass that face to our model. And that model predictor basically gives us a confidence value, which we can then sort of convert to a probability value of that face in a webcam being yourself. Just like this here. So now when you're standing in front of it, it should say a high confidence value that it is the user in question, which is what we trained it on here. And it will say unlock below. So that can be hooked up to unlock API on your system or cell phone. And if similarly, if someone else came in front of this view here, it will output a much lower confidence value. And then we can just set a threshold where it's unlocked or locked based on this confidence value. So let's see it in action. Alright, so let's go ahead and open our code. That's lecture 8.3, mini project number 10. And you will see 3 blocks of code here, 3 steps. So I've broken down the code into step 1, which creates our training data. So what this does, this uses hierarchy cascade classifiers here with our webcam, and basically I have a function called face extractor, which basically just crops the detected faces using hierarchy cascades and dumps it all here into a directory. Well, the function doesn't dump it here. The function just returns our cropped face. But this thing here, this code right here, actually resizes our faces to 200 by 200 to keep them uniform. And it just saves them into a path here. So you may have to create these directories first, so we can dump our 100 images there. So let's just run this code quickly and see how it works. Okay, so that's me being captured 100 times while I talk. This is quite fun. Let's wait for it to finish. Okay, there we go. So it successfully ran and says collecting samples complete. If for some reason you moved your face out of the picture frame, I just have an if then else statement here that says face not found, and it just waits for the face to come back in the image to continue capturing. Alright, so that's pretty basic and pretty simple. You should have understood most of that quite easily. So moving on to step 2 now, which is training our model. We firstly need to collect all those images of ourselves that we just stored. So that's what these 2 lines of code does here. So we use some of the OS library functions here. So we import it here. And what we do, we basically get all the file names in this directory here and store those file names in this variable or this array here called only files. And we basically loop through only files here, reading each image in the path here and storing it basically in a NumPy array here that we call training data. And we do so similarly for labels as well. So, and which is also converted into a NumPy array as well of this data type. So now we're ready to initialize our facial detection recognizer here. Remember, this is a linear binary patterns. So we initialize our model here by running this line of code here, and then we access the training, and then we basically feed our training data and labels into the model.train method right here. So that's pretty much it. So if we run this line of code, it's going to say model trained successfully in just a couple seconds, so that's pretty cool. Okay, so let's just do it one more time because I believe I did it out of view, and there we go, it's trained. So now let's move on to step 3, which is basically classifying images that we capture from our webcam again. So again, using our cascade classifiers, we use this function here to extract faces from the image in a webcam view, and that's standard code that you've seen before. So let's see what's going on here though. This area looks a little bit more interesting, and you'll see why. So basically, when we get a face image here, right, by collecting it from our face detector function, we then need to pass it to our prediction function. So as you saw, we created a model here, our model object, and that also has a predict function or method in it. So face would be our extracted or cropped face from this function, and basically model.predict returns a file called results, and results has two values. It's a tuple that gives us the confidence value and as well as label, so actually label and then confidence value. So our confidence value isn't a probability per se, it's actually a numeric value that goes all the way up to 350 or 500. So what happens here is basically once that value has been found or returned successfully, that's once there's a face in view, we actually just calculate our confidence value. So as I said, it went up to about 300 or 350 in my experience. Could be higher, but I have to look at the documentation behind this facial recognizer here. So let's just get a value here. So let's suppose, so basically lower is better. So what we do, we sort of calculate a pseudo percentage value, calling it confidence here, and then we create a string with that data here. And that's what we're going to output to the screen shortly, which you'll see very soon. That's what we use patex for. And how do we determine if the image is us or someone else? So that's why I've defined this threshold value here, 75, and you can play with this as well. You can make it very stringent and set it to like 85 or 90. However, I found 65 to 75 works fairly well. I'll demonstrate it very shortly as well. So basically, once this value exceeds 75, we display the string unlocked on our screen. Otherwise, we display locked. And also, if there's no face found in our screen, we just display no face found and also obviously display locked. So let's go ahead and run this code and see it in action. Okay, so let's run this. Okay, and you can see it's picked up my face and it's accurately giving me a high confidence value here. And it's saying unlocked, which is exactly what we wanted. And you can see as I turned here and my face went out of view, no face found locked. So how about we try someone else's view? How about we try Kim Kardashian? So let's get her in view here. And look at it, actually we get a negative value here, so we actually should make that 300 number larger, and it's saying locked. So clearly she is not me, and here I am. So this is actually pretty cool. You can try this with your friends and family. I tried it with my sister and my wife as well, and it did not recognize them. It did not unlock the computer when they sat in front of it. So that is pretty cool. So that is it for our very basic and simple facial recognition system. So I should just say this is a very, very simple dumbed down facial recognition program here. If you want to make something more sophisticated, I'm pretty sure you're going to have to use deep learning or convolutional neural nets or some deep belief network. So, but this is a good example for us to toy with and play with. And it actually does work in most cases. You can again toy with these values and try to get something better. It's up to you. So I hope you enjoyed this section and I hope you enjoyed this mini project. So we're now going to move on to object tracking.